Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. The sun rises in silence, but its presence is a chorus that has echoed through every age of life on Earth. Every morning, its gentle light spills over the horizon and washes the world in gold. In that light lies an ancient promise: warmth to nourish the living, energy to spark the green fuse of plants, and comfort to chase away the chill of night. For as long as creatures have walked under the sky, they have felt the sun's touch and known instinctively that this brilliant star is the giver of life. Yet the sun is more than a kindly nurturer. It is a colossal power, a raging sphere of fire suspended in the darkness of space. From across the cosmic void, it seems tame, a perfect golden disk that rises and sets with reliable grace. But up close, it is wild and untamable, a seething ocean of plasma and magnetic fury. It holds Earth in its grasp, guiding the dance of days and seasons. And it could, in an instant of cosmic anger, scorch our world lifeless. The same sun that gently warms our faces can also unleash deadly radiation and storms of charged particles. It is a giver of life, and it can be a destroyer of worlds. Our ancestors revered the sun as divine, calling it by many names and worshipping its life-giving light. They built great stone circles and temples aligned to its rising, celebrated when it climbed high in summer, and feared its waning in winter. In rare moments, when the sun vanished in a daytime eclipse, they watched in dread and awe as day turned to twilight, praying for the light to return. They sensed its dual nature, its generosity and its danger, even without knowing the science. We now understand that the sun is a star, one among countless others in the galaxy. But to us, it is unique. It is our star, the hearth of our solar system, the steady heartbeat of our cosmic home. It beats silently, a deep thrum of nuclear fires and magnetic pulses that we cannot hear, but that sustains us nonetheless. Every ray of sunlight is a note in that silent symphony, a connection between our small lives and the vastness of the cosmos. Consider this: the light that caresses your skin today began its journey at the core of the sun long before you were born. The warmth on your face is the end of a story that started deep in a stellar furnace. The sun bridges our brief human moment and deep cosmic time. It links the atoms in our bodies to the atoms in distant stars. In its light, we find both our origin and our destiny. We stand in the glow of a cosmic engine, often unaware that above us, a star's turbulent heart is burning and beating ceaselessly. To truly know the sun, we must journey into its very heart. Let us leave behind the blue of our sky and travel inward into the blinding brilliance, into the inner sanctum of our nearest star. What we find there is both humbling and wondrous, a story of creation and destruction, of light and darkness, of a star's life from birth to death. It is, in many ways, the story of ourselves, written in the language of light. Imagine plunging through the sun's surface and journeying toward its center. As we descend, the light intensifies and the heat becomes unimaginable. Deep inside, at the very core of the sun, we enter a realm of staggering pressure and temperature. Here in this stellar heart, hydrogen atoms are crushed together so tightly that they fuse into helium. In that act of fusion, a tiny bit of matter transforms into pure energy, an alchemy that powers the sun. This is the engine of creation hidden in the sun's core. Every second, an immense burst of energy is released, radiating outward to keep the star shining. Gravity presses inward relentlessly, trying to collapse the sun under its own weight. but the fury of nuclear fusion pushes outward, holding the star up. In this balance between gravity and fire, the sun's core burns steadily, a sphere of blazing plasma denser than solid iron and far hotter than any furnace on Earth. The core is a place of extremes beyond our experience. Its light is born in blinding abundance, yet none of that brilliance escapes directly. Only ghostly particles called neutrinos slip away unhindered, streaming out from the core and passing through the sun's layers, and even through our bodies on Earth, as though nothing were there at all. They are the silent heralds of the sun's heart, whispering of the nuclear fires within. Moving outward from the core, we enter the radiative zone, a vast internal layer where the energy from the core migrates slowly outward in the form of light. Here, photons of radiation ricochet through a dense maze of atoms. A single particle of light, born in the core's fury, may bounce countless times from one atom to another, absorbed and re-emitted in an endless random walk. The plasma in this zone is so opaque and crowded that progress for any ray of light is agonizingly slow. Ages pass as the energy inches its way outward. What we eventually perceive as sunlight on Earth has spent eons fighting its way through this hot, stifling labyrinth. In these deep regions of the sun, energy is transferred not in a simple beam, but like a traveler lost in a thick forest, zigzagging gradually toward freedom. Eventually, the character of the sun's interior changes. Further out, the stellar plasma becomes cooler and less dense, and it can no longer transport energy purely by the random diffusion of photons. At this point, a new process takes over: convection. We have entered the convective zone, the sun's outermost interior layer, where heat is carried upward by the motion of the gas itself. Picture an immense cosmic cauldron boiling slowly. Hot plasma from the layers below becomes buoyant and rises toward the surface, carrying energy with it. Upon reaching higher, cooler regions, it loses heat, becomes denser, and sinks down again to be reheated. These rolling currents form giant looping cells of plasma the size of continents, rising and falling in rhythmic surges. Through the convective zone, energy that once took millennia to crawl outward now surges toward the surface in a matter of mere weeks, riding the updrafts of this titanic, boiling motion. At last, the energy reaches the visible surface of the sun, the photosphere. This is the layer where the sun's light finally escapes into space and shines freely across the solar system. To our eyes, the photosphere is the sun's radiant face, a glowing golden disk with a sharply defined edge. Up close, it would not appear smooth at all, but finely textured and ever-changing. The surface seethes with the imprint of the convection below, a pattern of granules, like a vast mosaic of luminous cells. Each granule is the top of a convective plume, a cell of hot plasma rising from the depths. Their centers glow bright and white-hot, where fresh energy wells up, and their edges darken to a deeper amber, where cooler plasma is sinking back down. This granular pattern continually shifts and reforms, as though the sun's face is a living, boiling sea of light. Here and there, the photosphere is marred by dark blemishes, sunspots. These spots are cooler than their surroundings, and so they appear nearly black against the brilliance of the sun's face. A sunspot is born from the sun's magnetic mischief. Intense magnetic fields well up from inside the sun and suppress the hot rising gas, creating a region that is slightly less hot and thus darker. Sunspots can grow to be larger than the entire Earth and may last for days or weeks before dissipating. They are a sign that the sun's magnetism, though invisible, is ever present, knitting itself into the solar surface. We will soon see how these magnetic forces can erupt in violence, but for now, standing at the surface of the sun, we behold a roiling ocean of fire extending in all directions, a vista of constant boiling creation. Peering at the sun's face with sensitive instruments, we find that it is also vibrating subtly. The boiling convection within causes the sun to ring like a resonant bell. Its surface shivers in patterns, waves traveling across and through the sun, making the whole star gently pulse. Astronomers use these pulsations, this music of the sun, to probe its interior, much as one might learn the shape of a bell from the sound it makes. Through this solar symphony, we can discern the flowing currents deep inside, the building magnetic fields, and even hints of the sun's core, all hidden beneath the blinding glare. Rising above the photosphere, the sun's atmosphere continues outward in layers of increasing mystery. Just above the visible surface lies the chromosphere, a tenuous veil of gas that appears as a faint, pinkish glow. Here, the temperature, which had cooled at the photosphere, begins to climb once more. The chromosphere is like the sun's shimmering halo, visible clearly only when the bright photosphere is hidden during a solar eclipse. In those rare moments, it can be seen as a thin rim of ruby light encircling the moon's silhouette. Within the chromosphere, slender jets of plasma, called spicules, continually shoot upward, each one ephemeral and short-lived, lasting only minutes before falling back. The chromosphere is a restless transitional zone, a place where the fury from below meets the stillness of space above, and the solar atmosphere prepares for an abrupt and profound change. Above the chromosphere lies the sun's crown, the corona. Faint and otherworldly, the corona is a vast halo of pearly light that surrounds the sun and stretches far into space. It is breathtakingly beautiful and enigmatic, revealed to human eyes only during a total solar eclipse, or through specialized telescopes that block the sun's glare. In those brief eclipse moments, when daytime twilight descends and the moon hides the sun's brilliance, the corona appears as a pale, white aura, etched with luminous streamers and delicate filaments extending in all directions. But the corona is not merely a spectacle of light. It is a furnace in its own right, one far hotter than the sun's surface below. While the sun's photosphere is blisteringly hot, the corona above is unimaginably hotter, a puzzling reversal of what one might intuitively expect. In this outermost layer, the sun's magnetic field rules supreme, shaping the thin gases into graceful loops and arching structures. Great magnetic arches rise high above the sun, filled with incandescent plasma that traces the invisible lines of force. The corona is incredibly thin, its particles so sparse that if you were standing in it, shielded somehow from the heat, you might not even notice the few atoms brushing by. And yet, despite its tenuousness, the corona possesses immense energy and reaches temperatures of such magnitude that scientific instruments must strain to record them. Why does the corona burn so fiercely? It remains one of the sun's lingering mysteries. Perhaps the sun's tangled magnetic fields thrash and snap, heating the gas in a myriad of tiny explosions, or waves of energy ripple outward from the sun's surface, dumping heat into the corona. Whatever the cause, the sun's crown glows with an ethereal fire that science is still striving to fully understand, a reminder that even our well-known star holds secrets at its heights. At the edge of the corona, the sun begins to fade into the darkness of space. There is no sharp boundary where the star ends. Its atmosphere simply thins into the void. Here, the corona gives birth to the solar wind, a ceaseless stream of charged particles, electrons and protons, that flows outward in all directions. The sun, in effect, is always breathing out. Its breath is the solar wind, and it carries a piece of the sun's essence out to the farthest planets and beyond. The gravity that so overwhelmingly confines the core cannot hold these fast, lightweight particles of the corona. They race outward along open magnetic lines, escaping the sun's grip. The solar wind is, in a sense, the sun's extended atmosphere flowing freely into space, filling the solar system like an invisible, ever-expanding bubble. We have now traveled from the sun's core, where matter becomes energy, to the wispy fringes of its corona, where the star dissolves into the broader cosmos. In this journey, we have witnessed the anatomy of a star, its layered realms, each with its own wonders. We have seen the ferocious furnace at its center, the slow upward struggle of light, the boiling convection that brings energy to the surface, the radiant face shining into space, and the crown of fire that reaches beyond the sun itself. Yet the sun is far from a static ball of gas. It is dynamic and alive, its surfaces and atmosphere writhing with magnetic fields and sudden eruptions. To truly understand our star, we must explore these invisible forces that bind and sometimes unravel the sun's material. We must watch as the sun's calm radiance is punctuated by storms, blazing flares, erupting prominences, and billowing clouds of plasma that can span millions of miles. It is time to examine the sun's magnetic heart and the space weather it breathes into the solar system. Beneath the sun's bright face lies an unseen web of forces that drives its most dramatic behavior. The sun is a giant magnetic dynamo. As it spins on its axis and its plasma churns, it generates magnetic fields that thread through its interior and arch out into space. Imagine lines of unseen force looping out from the sun's depths, arcing high above the surface and diving back down. These magnetic field lines become twisted and tangled by the sun's constant turning and boiling. Where they burst through the surface, they drag up or suppress hot plasma, creating the dark sunspots we see freckling the photosphere. Every feature we observe on the sun, its spots, its flares, its glowing coronal loops, is shaped by magnetism. Without the magnetic field's influence, the sun would be a far more monotonous star. Instead, magnetism makes it a living, breathing, and sometimes tempestuous entity. Sunspots are the most visible signs of the sun's magnetic moods. They tend to appear in groups, often as pairs linked by a great looping magnetic field. One spot will have a north magnetic polarity, the other a south, like opposite poles of a bar magnet. The arc of magnetism connecting them traps cooler plasma in its grip, outlining structures we sometimes see as prominences, towering loops of glowing gas that stand above the sun's surface. Sunspots grow and shrink as the magnetic fields beneath them strengthen or decay. Over days or weeks, a complex sunspot group may evolve. An enormous energy builds up in its tangled magnetic knots. There is a rhythm to these appearances. Roughly every decade or so, the sun swings from a time of few sunspots to a time of many, and back again. At the peak of this cycle, dozens of spots can dance on the sun's face. At the low point, the sun's visage is often clear and quiet. Each cycle, the sun's magnetic poles even flip. North becomes south, and south becomes north, as part of this regular heartbeat of our star. Our sun, like a living thing, has its seasons of storm and calm. When the stress in twisted magnetic field lines becomes too great, they can suddenly snap into a new shape, much like a tensed rope that finally breaks free. In that instant, the energy that was bottled up in the field is explosively released. This is a solar flare. On the sun's surface, a flare is a blinding flash of brightness, a sudden blaze of radiation across the spectrum. It is as if a patch of the sun's surface has detonated with the power of countless nuclear bombs. In minutes, a flare unleashes a torrent of X-rays and charged particles into space. If the Earth lies in its path, these emissions race toward us at light speed, arriving just minutes after the flare erupts. Our planet's upper atmosphere suddenly swells with energy. Radio communications can crackle and fade as the ionosphere, the atmosphere's charged upper layer, is pummeled by the onslaught, and astronauts in orbit might hastily seek shelter from a burst of radiation that moments before was not even known to exist. Flares are often accompanied by an even more massive eruption, the coronal mass ejection, or CME. Where a flare is a flash of light and high-speed particles, a CME is a giant cloud of solar plasma hurled out from the sun. When a particularly complex magnetic loop in the corona destabilizes, it can fling away a chunk of the sun's outer atmosphere entirely. Imagine a colossal bubble of electrified gas, more massive than all of Earth's oceans combined, suddenly launched into space and expanding as it races outward. A coronal mass ejection can contain an astonishing amount of matter and energy, an immense, billowing stormfront in the emptiness of space. If one of these solar tsunamis is aimed toward Earth, we will know it soon enough. Within a day or two of the eruption, the wave of solar particles reaches our planet. Earth's magnetic field recoils and reverberates from the impact, like a bell struck by a hammer. We call this disturbance a geomagnetic storm. When a geomagnetic storm engulfs Earth, the results can be both beautiful and dangerous. Under the night skies at high latitudes, ghostly lights burst forth. Auroras, the northern and southern lights. Normally, auroras are confined to the polar regions, tracing the shape of Earth's magnetic field as it directs the sun's particles toward the poles. But during a strong solar storm, auroras can be seen much farther from their usual homes, painting the skies in eerie greens, purples, and reds over a vast swath of the world. Imagine waking in the tropics to find the night sky alive with rippling curtains of light. Such an astonishing sight has indeed occurred when the sun lets loose one of its great storms. In ages past, people who witnessed auroras far from the poles were often terrified. They saw in them dragons or celestial armies, believing the heavens were aflame with omens. To ancient peoples, these luminous dances in the sky must have been both wondrous and terrifying. Even today, knowing their true cause, one cannot watch the aurora's shimmering display without a feeling of reverence for the forces at play. Yet along with this beauty comes disruption. The same geomagnetic tempest that sets the skies aglow can wreak havoc on our modern technology. The barrage of charged particles and the distortion of Earth's magnetic field can induce surges of electric current in long conductors here on the ground. In our age of wires and wireless signals, a strong solar outburst can interfere with radio transmissions, scramble GPS navigation, damage satellite electronics, and even overload power grids, plunging cities into darkness. Over a century ago, a monumental solar storm made telegraph lines spark and catch fire. Telegraph operators found they could disconnect their batteries and still send messages. So powerful were the electrical currents coursing through the wires. If a storm of that magnitude struck today, satellites might be knocked offline, and extensive blackouts could occur. For all our technological might, we remain passengers in the sun's domain, subject to its occasional fits of violence. This turbulent interplay of solar magnetism and its effects on Earth and the planets is what we call space weather. Like weather in Earth's atmosphere, it has calm days and tempestuous days. The sun's magnetic field is ever shifting, and as it does, it breathes out gusts and squalls into the solar system. Most of the time, the solar wind blowing past Earth is a gentle breeze, and our planet's magnetic field shrugs it off with little fanfare. But when the sun erupts, the space around Earth becomes a stormy sea. A surge of charged particles and magnetic disturbances crashes against our planet's defenses, and near-Earth space itself reacts in kind. Auroras lighting up, satellites feeling the shock, currents coursing through the ground below, where all seems quiet. Fortunately, Earth has a sturdy shield. Our planet's magnetic field envelops us, carving out a protective bubble that the solar wind must flow around. This magnetosphere diverts most of the charged solar particles, allowing only a portion to funnel down toward the poles. In the clash of sun and Earth, the auroras are the glowing traces of our magnetic shield intercepting the solar storm, a testament to the protection it offers. Planets without a significant magnetic field, like Mars, have no such guard. Over eons, the sun's relentless particles stripped away much of Mars's atmosphere, leaving it a cold, arid world. In that fate, we see mirrored the dual nature of our sun, the gentle provider that sustained life on Earth, and the relentless force that can erode a planet's very sky. It nourished Earth with light and warmth, while its winds slowly wore Mars down. Magnetism is the hidden architect of the sun's behavior, from the steady cycle of sunspots to the wild drama of flares and auroras. Through it all, the sun continues to shine steadily in our sky, a reassuring beacon of day. But we have learned that beneath that steadiness is a flickering heart of magnetic energy. The sun's calm and its storms are two sides of the same coin, both born from the same stellar heartbeat. As humanity extends its reach into space and relies ever more on technology, studying and forecasting this space, weather becomes increasingly important. We now watch the sun with eyes open, tracing its spots and flares, listening for the whispers of its solar wind. We have even sent spacecraft to touch the sun's fringes, sampling its corona and feeling its magnetic embrace, all to better understand our star's moods. In the midst of these stellar tempests, it is easy to lose sight of the sun's most gentle and steadfast gift, the sunlight itself. Every day, countless photons leave the sun and stream across space, and some of those reach our world to illuminate the sky. Consider for a moment a single particle of light, a photon, born in the sun's core. It began as pure energy released by a fusion reaction in that dense, searing heart. For untold years, it fought its way through the sun's interior, scattering and dancing through the radiative maze, slowly migrating to the surface. At last, it broke free from the photosphere, joining the radiant tide of sunlight that floods out into the darkness. In that instant, it set out across the cosmic gulf at the ultimate speed, racing through the vacuum toward our small planet. After a brief voyage through the abyss of space, the photon pierces Earth's upper atmosphere. Perhaps it is dawn, and this tiny messenger of the day slips through a clear sky to reach a waiting leaf on a tree. The photon is absorbed, its energy triggering the chemistry of life, photosynthesis, helping a green leaf turn carbon dioxide and water into sugar. In that moment, a bit of the sun's energy, carried across the cold void by a single photon, becomes part of a living plant. Another photon falls upon a human face and is absorbed in the warm skin of someone standing under the morning sun. Nerves register the gentle heat. The mind welcomes the comfort. That warmth is a direct touch from our star, a tangible link between our flesh and the nuclear fires at the sun's heart. Every ray of daylight that we see, every soft beam reflected by the moon at night, began in the sun's core long ago. The sunshine that makes the petals of a flower glow, that draws a child's laughter on a bright afternoon, that dances on waves at dusk. All of it is energy forged in a star and sent outward as a gift across the emptiness. It is literally starlight. The light sustains the winds and rains of Earth's weather, drives the engines of life, and paints our world in color each sunrise and sunset. From the sun's perspective, these photons are a way it reaches into the darkness, touching worlds with its essence. From our perspective, they are life and time itself. Every meal we eat is sunlight captured by plants. Every sight we behold is enabled by the sun's illumination. Thus, the sunlight we feel on our skin carries an ancient story. It is the end of a journey that began in the heart of a star and a bridge between our everyday lives and cosmic processes. In that golden glow, the tumult of the sun's interior and the fury of its storms are gentled into a nurturing radiance that gives life rather than takes it. We are, in every sense, bathing in the light of a star. To stand in the sunshine is to be touched by the cosmos, to be warmed by a process that has been ongoing for eons. The next time you see dust motes dancing in a sunbeam or feel the sun's warmth on your face, remember that you are feeling the afterglow of a journey that spanned the depths of space and countless years, a journey from the core of a star to the core of your being. Beyond the orbit of Earth, the Sun's influence continues in a quieter but no less significant form. The solar wind that billows out from the corona fills the solar system with a tenuous, invisible presence. Space is not truly empty. It is filled with the Sun's breath. This stream of charged particles flows outward past all the planets, carrying with it a stretched-out imprint of the Sun's magnetic field. It's as if the Sun, through its wind, reaches out to touch each world in its orbit, linking them in a web of invisible threads. As the solar wind encounters each planet, the effects depend on whether the planet is protected by its own magnetic field or left exposed. We've seen how Earth's magnetic bubble deflects the wind, diverting the charged particles around us. Jupiter and the other giant planets have formidable magnetic fields that carve out even larger sanctuaries in the solar wind. When the solar wind presses against these magnetic bubbles, it sparks auroras at their poles too. Jupiter's polar skies glow with curtains of light far more intense than Earth's, and even Saturn wears ethereal rings of auroral light. On worlds like Mercury or our Moon, which have little or no magnetic shielding, the solar wind slams directly into the surface. It can embed particles in the soil and slowly sputter away atoms into space. Mars, with only patchy magnetic fields and a thin atmosphere, has its skies occasionally set aglow by diffuse auroras, a reminder that even without a strong magnetosphere, the solar wind still makes its presence known. Perhaps the most visually stunning evidence of the solar wind's reach is found in comets. When a comet from the frigid outer reaches of the solar system ventures close to the Sun, it sprouts a luminous tail that always points away from the Sun. This is because the solar wind, along with the gentle pressure of sunlight, is pushing material off the comet's nucleus and sweeping it into a tail that streams far into space. Every comet's tail is essentially a windsock, revealing the direction of the Sun's breeze. In ancient times, people saw those mysterious comets with their glowing tails stretching across the sky, and perhaps sensed that the Sun and the comet were interacting. Now we know it is the breath of the Sun, gusting through space, that draws those ephemeral streaks. The solar wind is not a steady, featureless breeze. It has structure and gustiness. Fast streams of solar wind can overtake slower ones, creating turbulent regions out in the depths of space. Magnetic clouds and shock waves from solar eruptions course through the wind, eventually overtaking planets or other spacecraft that lie in their path. The wind also carries the Sun's magnetic polarity outward. At times, Earth finds itself connected to the Sun by magnetic field lines stretching across interplanetary space, allowing energetic particles from solar flares to spiral directly toward us. In this way, the solar wind is the medium that transmits the Sun's influence throughout its domain, like a great cosmic ocean in which the planets sail. As our solar system journeys around the center of the Milky Way, it carries this protective bubble along. The Sun, like a bee in a giant swarm, orbits the galactic core among billions of other stars. One lap around the galaxy takes an unimaginably long time. In the Sun's long life so far, it has only managed a few dozen such circuits. On this grand voyage, our star drifts through changing cosmic neighborhoods. Sometimes the space around it is relatively empty. At other times it might encounter wisps of nebulae or the lingering echoes of ancient supernovae. These encounters can subtly influence the boundary of our heliosphere, perhaps even nudge comets from the distant cloud at the fringes of our solar system. We ride along on this stellar odyssey, a family of planets wrapped in the Sun's embrace, cruising through the galaxy's spiral arms. It is a humbling thought that our entire existence, every life, every story told under the Sun, has been carried on this great galactic journey, and it will continue long after we are gone, the Sun forging ahead through the dark with its tiny companions in tow. Eventually, at some immense distance from the Sun, the solar wind begins to meet resistance. The sparse gas that drifts between the stars pushes back against the sun's advancing wind. The solar wind slows, compresses, and finally, at a certain boundary, it can push no further. The continuous expansion of the sun's atmosphere is halted by the presence of the wider galaxy. This boundary marks the outer edge of the sun's influence, the frontier of our star's dominion. Here, the solar wind's long journey ends, merging into the interstellar medium. This invisible border defines a vast bubble around the sun, known as the heliosphere, a cocoon of solar particles and magnetic fields that envelops all the planets. To step outside that bubble is to enter truly interstellar space. For decades, the solar wind was only a theory, an idea to explain why comet tails always point away from the sun. It wasn't until humanity ventured into space with probes that we felt this wind firsthand. Our spacecraft have measured its particles and tasted its composition. Finally, after decades of journeying, a tiny spacecraft built by human hands passed through the boundary of the heliosphere and sailed into interstellar space, becoming the first emissary from Earth to enter the realm between the stars. It confirmed the existence of that distant frontier and carried with it a golden greeting from our world as it moved under the dim light of a sun now far behind. The sun's breath, it turns out, has a limit. Within that limit, within that bubble, the sun is Lord and life-giver. Every world we have ever known lies inside this protective sheath blown by our star. Now, standing at the edge of the heliosphere, we gaze outward and backward to the realm of the galaxy beyond, and backward toward the sun at the center of its bubble. We can appreciate the true scale of our star's influence. The sun is not just a disk in our sky. It commands a vast region of space, sculpting it with light and wind. It has forged a safe haven in the galactic sea, a place where its family of planets resides. To understand the sun fully, we must also understand how stars like it are born and how they die. For our sun is one among billions, each with its own story of origin and fate. Our journey now moves beyond our solar system, beyond the present moment of our sun's life, to the story of how such stars come into being and how they transform over time. Stars are born in darkness, far from the bright bustle of any galactic core, in the quiet spiral arms of galaxies like our Milky Way. Vast clouds of gas and dust drift in cold obscurity. These are the stellar nurseries, enormous nebulae stretching across light years of space, rich in hydrogen and sprinkled with heavier elements forged in ancient supernovae. Within these great clouds, gravity works patiently and silently. A slight densification, perhaps triggered by the shockwave of a distant exploding star or the brushing encounter of two clouds, begins to draw matter toward its center. As the gas compresses, it heats up and starts to glow faintly. What was once invisible in the darkness becomes a warm ember hidden inside a cocoon of dust. This is the birth of a star, or rather, the first whisper of a star yet to be. As the cloud fragment collapses under its own weight, it often breaks into smaller pieces, each destined to form a star, or even a small cluster of stars. In each fragment, matter spirals inward, and as it falls, it begins to spin faster, like a twirling ice skater pulling in her arms. A flattened disk of gas and dust forms around the growing central mass, whirling like a carousel. At the center of each collapsing fragment, a protostar, a baby star, is taking shape. It is not yet a true star, for it has not begun nuclear fusion, but it shines with the heat of its gravitational contraction. We can imagine it as a glowing orb buried deep within a dusty womb. If we could pull back the veil of dust and look inside, we would see a scene both serene and violent. The protostar's surface roiling with convection, jets of gas erupting from its poles and piercing out into space, and the surrounding disk feeding material steadily onto the growing stellar infant. In these concealed cradles, many stars are often born together, siblings in a stellar brood. Some are destined to be massive and brilliant, others small and faint. For a brief time, the protostar continues to gather mass. The infalling gas rains down mostly onto the disk, which then funnels onto the star. The star grows, and the pressure and temperature at its center climb ever higher. When the core temperature at last soars to the threshold, where hydrogen atoms begin to fuse into helium, a profound transformation occurs. The protostar becomes a star. It is as if a switch is flipped in its core. The darkness inside ignites into light. The star begins to generate its own energy by the same nuclear process that powers our sun, and a new sun bursts into existence in that once dark place. With that first ignition of fusion, a stellar wind, much like the solar wind of our sun, often springs from the newborn star, and intense light from the hot young star pours into the surrounding space. These forces blow away the remaining shreds of the natal cloud, dispersing the cocoon that once hid the star. If the star is massive enough, its fierce radiation may carve fantastic shapes in the parent nebula, creating glowing cavities and pillars of dust that resist the onslaught for a time. Before long, what was once an opaque dark cloud becomes a cluster of shining new stars, its birth cloud eroded to wisps around them. The siblings now bask in each other's light as they drift together, loosely bound by gravity. Our own sun was likely born in such a cluster of stars. It may have had many siblings forming alongside it in a long-vanished nebula, all of them cocooned together and then emerging into the galaxy's light. In that stellar nursery, the sun's siblings would have shone nearby, sharing a common region of space for a time. But over the ages, the cluster dispersed. Each star, including our sun, went its own way, moving through different orbits around the Milky Way. Today, the sun's sisters and brothers are scattered, indistinguishable from the other stars of the galaxy, though astronomers scanning the sky have identified a few stars with chemical fingerprints so similar to the sun's that they might be long-lost solar siblings. In the collapse of a nebula and the birth of a star, we see nature's cycle of creation at work. The gas and dust that form new stars carry the ashes of previous generations, the carbon that will someday course through the veins of living creatures, the oxygen that will fill their lungs, the silicon that will form rocky worlds. All these atoms were fused in stars that lived and died before our sun was born, then mixed into the clouds from which new stars arise. Each generation of stars enriches the galaxy further, seeding the raw material for planets and life. Thus, when a new star like our sun ignites, it carries within it the legacy of cosmic ancestry. Around many newborn stars, the leftover gas and dust in the disk coalesce into smaller clumps, giving birth to planets, moons, comets, and asteroids, the makings of a new solar system accompanying the new sun. From afar, a stellar nursery like the Orion Nebula offers us a glimpse of this wondrous process. Through telescopes, we see stellar embryos still swaddled in dust, others breaking free and burning blue-white with youthful energy. We see great columns of dark gas, cosmic pillars, being eroded by the radiation of hot young stars hidden within them. In that radiant chaos, worlds are being formed, and light that will shine for billions of years is first kindled. Starbirth is at once delicate and cataclysmic. Delicate in the slow, inexorable gathering of a star's first light, and cataclysmic in the way a newborn star's brilliance can rip apart the very cloud that gave it life. From these nurseries emerge all stars, whether destined to be mighty blue giants or dim red dwarfs. The process is the same, guided by the pull of gravity and the laws of physics that govern heat, pressure, and fusion. We have journeyed from our sun's neighborhood out into the broader galaxy to witness the origin of stars. Now, having seen how stars take their first breath, we can explore the grand tapestry of stellar variety. the many kinds of stars that fill the cosmos, from the smallest embers to the most luminous beacons. The stars that populate the universe are as diverse as the creatures in a great ocean. They come in different sizes, colors, and brightnesses, each type with its own character. Astronomers classify stars by their temperature and luminosity, which often correlates with color. Just as iron glowing in a blacksmith's forge changes from dull red to orange to white hot as it gets hotter, a star's color tells us its heat. The coolest stars are deep red, smoldering with a subdued cherry glow. Hotter stars shine in yellow and white hues. The very hottest stars blaze with blue-white brilliance, their surfaces incredibly hot. The smallest true stars in the cosmos are the red dwarfs. These diminutive stars contain only a small fraction of the sun's mass and glow feebly, often with a light so faint that none are visible to the naked eye from Earth, despite being the most numerous stars in the galaxy. A red dwarf is usually much smaller and cooler than our sun, giving off a ruddy light. But what they lack in brightness, they make up in longevity and ubiquity. The vast majority of stars in the Milky Way are thought to be red dwarfs, quietly burning their fuel at a glacial pace. A red dwarf may live for an almost eternal span of time before it runs out of fuel. In these diminutive furnaces, the flame of nuclear fusion is weak but extraordinarily steady. Some of the smallest red dwarfs can continue to shine for longer than the current age of the universe. On the other end of the stellar spectrum are the blue giants and supergiants. These stars are born with many times the mass of the sun. They are extremely hot and brilliant, shining with a fierce blue-white light that can be seen across great distances. A blue giant star pours out an enormous amount of energy, consuming its hydrogen fuel at a prodigious rate. Because of this, its life is intense and fleeting. It will exhaust its core fuel in a cosmic eye blink, a mere moment compared to the tranquil longevity of a star like our sun. Some of these massive stars do not stay blue-white for their whole lives. As they age, they swell and cool, turning into red supergiants that can be truly colossal in size, their bloated atmospheres expanding outward to stupendous dimensions. Imagine a star so large that, were it placed where our sun is, it would extend beyond the orbit of Earth and well into the realm of Mars. These red supergiants glow with a cooler, reddish light, but they are tremendously luminous due to their sheer size. They are rare and splendid beacons in galaxies, heralds of impending cosmic change, for they live fast and die spectacularly. Between these extremes lies a rich variety of stars. There are orange dwarfs, slightly smaller and cooler than the sun. There are white stars, somewhat hotter and more massive than the sun. And there are stars like our own, yellow-white and medium-sized, often called main sequence stars or dwarf stars by astronomers. Our sun, in fact, is considered a dwarf star in this sense, not because it is especially small, it is larger and more massive than most stars, but because it is in the prime of its life, steadily fusing hydrogen in its core. It hasn't yet bloomed into a giant. In terms of mass and brightness, the sun is fairly average, but because the faint red dwarfs are so inconspicuous to our eyes, most of the individual stars that dazzle us in the night sky are actually more luminous than our sun. Many of the bright stars we see at night are larger, hotter, or more energetic than the sun, which is why they stand out from afar. Meanwhile, countless dim red stars nearer to us go unnoticed without a telescope. Stellar classification also includes exotic categories. There are the supergiants we mentioned, both blue and red, which are essentially stars on steroids, far larger and more luminous than ordinary stars. And there are stars at the very brink of not being stars at all, the brown dwarfs, sometimes nicknamed failed stars. These objects form in the manner of stars but do not accumulate enough mass to ignite sustained hydrogen fusion in their cores. A brown dwarf glows faintly with leftover heat from its formation, and perhaps with brief flashes of fusion of heavier forms of hydrogen, but it gradually cools and fades, acting more like a giant planet than a true star. Brown dwarfs fill the gap between the largest planets and the smallest red dwarfs, and they add to the menagerie of objects in the galaxy. Nature produces stars in a continuum of masses and sizes, from tiny red embers that burn for practically eternity to stellar titans that blaze with incredible intensity and then perish in the blink of an eye. Each type of star has its own destiny. A star's mass, set at birth, is the key that unlocks the rest of its life story. With a high mass comes a glorious but short-lived existence as a giant, likely ending in a dramatic explosion. With a low mass comes a long, steady burn and a quiet retirement. Having surveyed the variety of stars, the small, the medium, the great, we can now follow one typical star, perhaps not unlike our Sun, through the stages of its life, from its youthful radiance to its final farewell. Let us trace the fate of a star much like our Sun, now that it has burned in the heavens for eons. For a long time, such a star shines steadily, fusing hydrogen into helium in its core and bathing any nearby worlds in stable light. But the fuel at its center is finite. Eventually, after many billions of years of shining, the hydrogen in the core dwindles. The balance that sustained the star for so long begins to tip. With less fusion to support it, the core of the star starts to contract under its own gravity. As it contracts, it heats up, much as a bicycle pump grows warm when you compress the air inside. This extra heat flows into the shell of hydrogen that surrounds the inert core, a shell that still has hydrogen left to burn. And then something dramatic happens. Hydrogen in this outer shell, now at extreme temperatures thanks to the contracting core beneath, ignites in fusion. The sudden onset of shell burning causes the star's outer layers to push outward. The star swells enormously in size, turning into what we call a red giant. Its surface cools as it expands, shifting from yellow-white to orange-red. But the star's interior becomes hotter than ever, and its luminosity soars due to its sheer size. Our once modest sun-like star becomes a bloated colossus. In this red giant phase, the star's radius can grow far larger than it was in its youth. If our Sun were to undergo this transformation, it would likely engulf Mercury and Venus, and perhaps even Earth, turning those worlds into charred cinders swallowed by the expanding stellar fire. The sky of any surviving outer planets would be dominated by the star's enormous disk, a brilliant coppery orb covering a huge swath of the heavens. Deep inside the red giant, the core continues to shrink and heat, as it is now made mostly of helium ash, the byproduct of those long ages of hydrogen fusion. When the core grows hot enough, a new kind of fusion begins. Helium atoms start fusing together to form carbon and some oxygen. Our star, which was facing death, finds a second wind. The onset of helium fusion in the core, often beginning in a sudden burst for a sun-like star, something astronomers poetically call the helium flash, stabilizes the star for a time. The core expands a little and cools, and the star's bloated outer layers contract somewhat from their extreme size. The star settles into a new equilibrium, a helium-burning giant. In this phase, the star's color might become a bit more yellowish as it slightly shrinks, and its surface temperature rises again, and it burns steadily once more, though its remaining lifetime is now comparatively brief. But helium, too, is a finite fuel. In time, the core's helium is exhausted, leaving an inert mass of carbon and oxygen, the carbon and oxygen that were created by the helium fusion. For a star like our Sun, no further fusion is possible in the core. The temperatures required to ignite carbon are beyond its reach. With fusion ceasing again in the center, the core of the star, now a dense ball of carbon and oxygen, contracts yet further. Meanwhile,
Helium fusion may continue in a shell around the core, with hydrogen fusion still going in a shell above that for a while. This causes the star to swell once more, even larger than before. The giant star becomes highly unstable in this final stretch of its life. It pulsates, growing and shrinking, trying to find balance, but never quite succeeding. Each expansion and contraction shakes loose some of the star's outer layers. Gentle at first, these pulsations turn into violent throes that throw vast clouds of the star's outer atmosphere into space. The star is literally coughing away its own substance, shedding its mass like tears into the void. Eventually, the entire outer envelope of the star is cast off, blown away into space as a gorgeous gossamer shell of gas. For a brief time, that expanding shell is illuminated by the hot, exposed core at the center, and it shines as a glowing, multicolored cloud known as a planetary nebula. To an observer afar, it is a sight of eerie beauty. A round or ring-shaped mist, glowing where once there was a star, often with intricate patterns like delicate rings or hourglass forms. This is the dying breath of a star like the Sun, a final gesture of beauty as its outer layers, now free in space, fluoresce in the stellar twilight. What remains of the star itself is the central core, now revealed, a ball of carbon and oxygen about the size of Earth, tremendously hot but no longer sustained by fusion. This is a white dwarf, the ember of a star's heart. It glows white-blue with residual heat, initially extremely hot, though its small size means its total light output is relatively modest. A white dwarf is one of the strangest forms of matter in the universe. It is supported not by heat or ongoing fusion, but by the quantum pressure of electrons, a fundamental resistance of matter to further compression. Its density defies imagination, the mass of a sun compressed into a sphere the size of a planet. A spoonful of white dwarf material would outweigh a mountain. In this exotic, degenerate state, the stellar core will sit and slowly cool for time spans beyond human comprehension, fading from white to yellow to red, and eventually toward blackness. Thus ends the life of a sun-like star, not with a bang, but with a serene farewell glow. The mighty red giant's cast-off shroud becomes part of the galaxy, seeding space once more with elements like carbon and oxygen that will one day find their way into new nebulae, new stars, new planets, and perhaps new living beings. The white dwarf that remains is like a stellar tombstone, an extremely dense crystal of carbon and oxygen. Some have likened a white dwarf to a cosmic diamond, marking where a shining sun once lived. Over eons, it will cool further and dim, eventually becoming a black dwarf, a hypothetical cold dark sphere, the final quiet cinder of a once radiant star. The universe, however, is not yet old enough for any white dwarfs to have cooled completely to black. That final stage lies in the far future, far beyond the present age of the cosmos. Our sun will one day follow this very path. It is the destiny of all stars in its weight class. But not all stars share the same fate. The most massive stars, those bright blue giants we discussed, live dramatically different lives and meet far more violent ends. Before we return to the personal tale of our own sun's future, let us first briefly touch on the spectacular final act of those heavier suns, a fate that leaves behind some of the most enigmatic objects in the cosmos. While a star like the Sun ends its life in relative peace, the same cannot be said for the giants. The most massive stars go out with staggering violence. After burning through hydrogen and helium in a cosmic rush, a high-mass star, far more massive than our Sun, doesn't stop at carbon and oxygen. Its core, under tremendous gravity, continues fusing heavier and heavier elements in layers, like the layers of an onion. Carbon fuses into neon, neon into oxygen, oxygen into silicon, each stage burning faster and yielding less energy than the last. Finally, the core is transmuted into iron, the ash of nuclear fusion, an element that cannot release energy by fusing further. When enough iron accumulates in the core, the star faces an irreversible crisis. With no new energy to support it, the iron core collapses in on itself in a fraction of a second. The core implodes, and densities reach such extremes that atoms are crushed. Protons and electrons melt into neutrons. The core, which was once perhaps the size of Earth or smaller, shrinks to a sphere only a few miles across in an instant. In that moment of collapse, a phenomenal amount of gravitational energy is released. The infalling outer layers of the star hit this super-dense core and rebound outward in a titanic explosion, a supernova. The star's death throes are so violent that for a brief time, the exploding star can outshine all the billions of other stars in its galaxy combined. The supernova blasts the star's outer layers into space at incredible speeds, and shockwaves race through the expanding debris. Temperatures in the explosion briefly soar so high that elements heavier than iron are forged in the fiery crucible. Gold, silver, uranium, and many others are synthesized in those final furious seconds. These newly minted atoms are hurled into the cosmos to mingle with the gas and dust that will eventually form new stars and planets. What remains at the center of this cataclysm is the collapsed core. If the star was only moderately massive, on the lower end of the massive star range, the core's collapse is halted by the pressure of densely packed neutrons. Matter squeezed so tightly that the neutrons resist any further compression. The core becomes a neutron star, an object of incredible density and exotic nature. A neutron star packs more mass than our Sun into a sphere only a few tens of miles wide. It is essentially a giant atomic nucleus, a ball of neutrons left behind by the supernova. A thimbleful of neutron star material would outweigh a mountain. Neutron stars often spin rapidly. The parent star's rotation speeds up dramatically as it collapses, like a pirouetting skater pulling in her arms, and they may possess intense magnetic fields. Some neutron stars sweep beams of radiation from their magnetic poles as they spin, like lighthouses in the cosmos. These are observed as pulsars, blinking radio or X-ray beacons, marking the location of a neutron star across the galaxy. For the most massive of massive stars, even neutron degeneracy pressure cannot hold the core up. If the collapsed core is above a certain critical mass, nothing known can stop its collapse. It continues to shrink until it essentially vanishes from view, forming a black hole. In that case, the stellar remnant has crushed itself into a point of virtually infinite density, enveloped by a region of space from which nothing can escape. Not even light can climb out of the warped space around the collapsed core, hence the name black hole. What was once the heart of a star becomes a kind of cosmic abyss, a pit in the fabric of the universe. A black hole can be thought of as the star's ultimate tombstone, carrying its mass hidden within a distortion of space-time. We infer its presence only by ghostly tracers, the desperate whirl of gas and dust spiraling into invisibility, flaring in X-rays as it vanishes, or the subtle quivering of space-time itself when the black hole is jarred by the fall of something massive. When a supernova finally fades, it leaves behind these strange remnants, a neutron star or a black hole, and an expanding cloud of gas and dust that was once the star's outer layers. In time, that cloud will cool and disperse into the interstellar medium. The elements cast into space will blend with other matter and eventually become part of new stars, new planets, and perhaps new life. Massive stars, though few in number compared to red dwarfs, are the great alchemists and fireworks of the universe. In dying, they sow the heavy elements across the galaxy, the very elements that make rocky planets and organic beings possible. Every atom of calcium in your bones, of iron in your blood, was forged in the belly of a star that ended in such a blaze. The cosmic ashes of supernovae fertilize the galaxies, ensuring that each new generation of stars is born with a richer array of ingredients for planets and for life. We have traced the lives of stars from gentle birth in nebulae to either a quiet sunset as a white dwarf or a cataclysmic finale as a neutron star or black hole. But our exploration of suns would be incomplete without considering that stars rarely live in isolation. Most have companions or families of their own, multiple star systems bound in gravitational dances or retinues of planets that circle around them. Our sun itself has a family, the planets, including Earth, and smaller bodies that formed from the disk of dust left over from the sun's birth. And many stars form in pairs or trios, locked in orbits around each other. To truly understand the nature of suns, we must also look at these relationships, the celestial communities that stars form, and the diverse planetary systems that have arisen around distant suns. Each star in the night sky is a sun in its own right, and many are far from solitary. In fact, most stars are born as multiples, two or more suns bound together by gravity, orbiting a common center. Imagine a binary star system, two suns locked in an elegant dance, circling each other over years or centuries. From a distance, they might appear as a single point of light, but up close, each partner star swings through space in response to the other's pull. Some binaries are widely separated, each star carrying its own retinue of planets. Others whirl so close that they can trade gas, or even, in extreme cases, merge into one. In a triple or quadruple system, the dance grows even more complex, with stars tracing intricate paths around their mutual center of mass. The universe is a grand stage, with every stellar configuration you can imagine. There are suns that eclipse one another from our viewpoint, causing their combined light to rhythmically dim and brighten, cosmic beacons signaling their orbital waltz. There are stars so close that they share a common envelope of gas, two stellar hearts wrapped in one glowing shroud. And there are systems where small companion stars orbit giant ones in distant loops, like tiny sparks flitting around a great flame. Around many of these suns, planets coalesce and circle, for planet-making is a natural companion to star-making. When a star is born from a spinning disk of dust and gas, the leftover material often forms worlds. Our own solar system is one example, a handful of major planets and a retinue of smaller bodies. And we have learned that planets are astonishingly common. We now know that planets accompany stars throughout the galaxy. Astronomers have discovered innumerable exoplanets orbiting distant suns, and they suspect that for every star we see, there are likely worlds in attendance. There are planets that cling close to their stars, scorched and locked by gravity, so that one hemisphere endures endless day while the other is in perpetual night. There are planets at just the right distances from their suns, the so-called habitable zones, where conditions might allow liquid water and the chemistry of life. Some planets orbit twin suns, experiencing double sunrises and double sunsets, their skies graced by two stellar disks. Imagine standing on such a world, with two faint shadows dancing on the ground, or on a world under a dim red dwarf sun, where the daylight is a brooding ember, and the stars' frequent flares paint the sky with sudden ruddy hues. Each planetary system is a story of creation, just as every star's life is a story. Some stars have giant guardian planets that shield inner worlds from comet bombardments, as Jupiter helps shield Earth. Others have planets in wild, elongated orbits, leading to chaotic swings of climate. Some massive stars might not host long-lived planets at all, as their fierce radiation and short lives can blast away or outlast any nascent worlds. But around the more common, steady stars, the red dwarfs, the orange dwarfs, the sun-like stars, there are surely many planets that have persisted for eons, perhaps even giving rise to life. Under alien suns, if life has blossomed, creatures might gaze up and see a sky tinted by a different color of star and wonder about the warmth that gives them life.
just as we ponder our sun. For us, those other suns have been points of curiosity and imagination for as long as we've had eyes to see the stars. Only recently have we begun to detect some of their planets directly, to see the telltale dip in a star's light as an orbiting world passes in front of it, or to measure the slight wobble of a star tugged by the gravity of unseen companions. Each discovery is a revelation, proof that our sun and its family are not unique, that the cosmos is filled with solar systems. It humbles us, yet also makes the universe feel more intimate. A place where countless stars shine down on their own worlds, as the sun does on ours. Now, after journeying so far through stellar nurseries, fiery demises, and distant solar systems, we return our focus to our own star, the sun, and reflect on its ultimate destiny, and on what it means for us to live beside a star. And so we return to our sun, the star that has accompanied every moment of humanity's existence and that sustains all life on Earth. The sun today is a middle-aged star, steadily burning its fuel and kindly bathing our world in light. It has shone in our skies for longer than any living thing can remember, and will continue to shine for ages to come. But the sun, too, is mortal in the cosmic sense. Nothing in the universe lasts forever, not even a star. In the far future, long after our species and all we know may have turned to dust, the sun will begin to change. When its core can no longer sustain the fusion of hydrogen, it will respond by growing in size and luminosity. Our sun, so familiar and constant, will swell into a red giant. Its light will turn the color of copper and blood, and it will loom colossal in the sky. The innermost planets will be engulfed in its fire. Mercury and Venus will surely be devoured. Earth may meet the same fate, or be left a charred and barren rock, its oceans boiled away, its surface desolate and scorched. For any life remaining then, these changes will be catastrophic beyond measure. But likely, by that distant era, Earth will already be quiet and lifeless, or life, if intelligent and capable, will have found refuge elsewhere. The sun, once a gentle guardian, will become an inexorable destroyer of the very life it once nurtured. Yet even in this fierce transformation, there is a strange grandeur. As the sun's red giant phase reaches its climax, it will cast off its outer layers. Our star will shed its shining mantle, which will expand outward, drifting into space. For a short time, those cast-off layers will form a beautiful planetary nebula around the dying sun, a glowing testament to its passing glory. Future astronomers, perhaps from other surviving worlds or civilizations yet unimagined, might look toward our solar system and see a delicate shell of gas, like a cosmic flower blossoming and fading, shining in remembrance of the star that was. At the center of that nebula will remain the sun's core, now exposed and shrunken to a white dwarf. This final stage of our sun's life will be a small, hot sphere no larger than Earth, composed mostly of carbon and oxygen. The sun's very heart, left glowing like a lonely ember in the night. It will shine white and then blue-white, slowly cooling over the course of billions of years. The brilliance of the day that once was will recede into a gentle twilight. The white dwarf sun will illuminate the ghostly nebula for some thousands of years, but eventually it too will fade, perhaps becoming a black dwarf in the far, far future. The solar system will drift in darkness and silence. This is the ultimate fate of our sun, to swell in glory and then to divest itself of its brilliance, leaving behind a small, dense core that will quietly glow and then dim to darkness. It is a fate that the sun will meet far in the future, an inconceivable gulf of time beyond our lives. In knowing this, we find both melancholy and solace. Melancholy that all things we know are transient, that even the great sun will one day wither and leave the sky empty. Solace that we and our world have yet long epochs in which to live under the sun's light, and that when the end comes, It will be part of the natural order of the cosmos. The same finale that countless sun-like stars have already played out in the quiet reaches of the galaxy. And perhaps, too, there is a kind of triumph in this ending. The sun's final nebula will return its substance to space, enriching the interstellar clouds with elements that once made up Earth and us, and every living thing that sunlight ever touched. In that way, the sun's death will seed new beginnings elsewhere. Some of the carbon and oxygen from the sun's core might drift for ages and eventually become part of new stars, new planets, new life. As it has always been in the universe, one star's end is another's beginning in the endless cycle of creation. Now, stepping back from this entire journey, from the birth of stars in dark nebulae to the blaze of supernovae, from the quiet glow of the sun's youth to its fiery demise, we find ourselves contemplating what it means to be the children of a star. To live beside a star is to live in a state of grace between wonder and knowledge. We orbit a massive, luminous being that gives us everything: light, warmth, the very possibility of life, and yet asks nothing in return. Our ancestors felt the sun's power and worshipped it. They built legends and monuments to honor it. We, with all our modern understanding, have not lost that reverence. How could we? Each dawn when sunlight spills over the horizon, painting the sky in rose and gold, we feel the same awe that ancient watchers felt as the morning star ascended. In that daily miracle, night yields to day, cold yields to warmth, and the world is renewed. We know the science of it. The earth is turning, bringing us once more into the sun's light. But knowing takes nothing away from the magic of feeling it. Beneath the facts and figures, there is a simple truth. The sun is the source of our being. Every meal we eat is sustained by sunlight captured by plants. Every warm breeze that caresses our skin, every drop of rain that falls, is driven by the sun's heat, nurturing our planet. And our bodies themselves are made of material created in long-dead stars and powered by the sun's current light. We truly are made of stardust, shaped into conscious form and given the spark of life by a star's energy. In a very literal sense, we are children of the stars. When we say we are born of starlight, it is not just poetry, it is lineage. The elements in our flesh were brewed in stellar furnaces, and the energy that ignites our living cells is a gift from our sun. Our story and the sun's story are inseparable. Think of the connection. A baby born on a bright morning, crying out with lungs filled for the first time. Those lungs draw in oxygen that a star, billions of years ago, forged in its core and then cast into space. The baby's parents smile in the sunlight that streams through the window. Sunlight that left the sun just moments earlier, having traveled across empty space to fall upon that new face. A chain of events spanning eons and light years has culminated in that ordinary, extraordinary moment. Starlight becomes life. The cycle continues. Standing here on Earth, we look up and see a blue sky by day. But beyond that blue lies the black tapestry of space and the brilliant stars. Our sun is one among many, and though we cannot see those others by day, they are there, distant and shining. At night, when our sun has set, we glimpse the wider cosmos of which our star is a part. We see the Milky Way's misty band, made of uncountable suns, and we realize that our little home orbits just one humble star on the edge of a vast galaxy. The humility of this perspective is profound, yet it does not diminish us. It elevates us. We are part of something immense and beautiful. The stars that speckle the night sky are our cousins. Some may have planets with beings who look up at their own sun and feel the same wonder. In the end, the story of suns is the story of creation itself. It is an ancient tale, told in the language of light and gravity. It began before we were here, and will continue long after we are gone. But for a brief moment, we get to be conscious participants in this grand drama.
We get to study the sun, protect ourselves from its tantrums, bask in its warmth, and dream under its light. Our lives, like mayflies, flicker in the daylight of this star. But while we are here, we behold the splendor of the cosmos through the window that our sun's light provides. As we conclude this journey, imagine once more the sun hanging low at dusk. The sky blazes with color, and the shadows grow long. In that sunset is a reflection of the entire epic. Day turning to night as stars appear one by one, the cycle of light and dark that has guided life's rhythm from the beginning. The sun will rise again tomorrow, as it always does, bringing a new day. But even when it eventually rises no more, the legacy of its light will live on in everything it touched. We live on the brink of a star's fiery grace, taking our nourishment from its hand and daring to learn its secrets. We are small, but we are also a way for the universe to know itself. Matter that was once scattered across space, now gathered and alive, pondering the star that gave it life. In the dance of sunlight and shadow, we find meaning, comfort, and inspiration. Our sun connects us to the universe and to each other, a common star, binding all living things in a shared radiance. So when you next stand in daylight, feel that warmth and remember, you are heir to an ancient covenant between Earth and Sun. Every photon that touches you carries a message from that central fire, that life is precious and intertwined with the cosmos. Our world exists because a star shines. And in the atomic hearts of stars, in the silent roaring of their nuclear fires, in the gentle glow that crosses the void, the universe has found a way to nurture consciousness and wonder. This knowledge, this feeling, is humbling and uplifting all at once. The saga of suns is indeed a cosmic poem, forged in light, breath, and gravity. It is written across the heavens in the glow of nebulae and the ashes of supernovae, in the rising of each morning sun and the eternal glitter of the night. It is a poem we are part of, every one of us made of star stuff and sustained by starlight. In knowing this, we find not despair at our smallness, but gratitude and awe that we have the privilege to dance in the light of a star, and through that light, to glimpse the eternal. We speak of everything, yet we hardly grasp its magnitude. Everything is the totality of existence, the stars and galaxies, time and space, energy and matter, life and mind. It is all that ever was, all that ever will be. In its embrace are the quiet dust under our feet and the shining furnaces of distant suns, the hum of a thought and the roar of a supernova. To contemplate everything at once is to stand at the shore of an infinite ocean, awed and humbled. Even our most fleeting reflection on the cosmos can send a shiver down the spine, as if some deep part of us remembers that we are a part of this grand tapestry, woven into its very fabric. On a clear night, under a vault of stars, we gaze upward and attempt to fathom our place in a vastness without obvious bounds. We see pinpoints of light scattered across a canvas of darkness, each a sun, perhaps with its own planets and stories. We feel small, yet we are connected to all of it. The iron in our blood, the calcium in our bones, the carbon in our DNA, these were forged in the hearts of ancient stars. We are children of the cosmos, built of its matter, energized by its light, and guided by our curiosity to understand it. Through science and imagination, we stretch our minds toward the edges of the universe, seeking to grasp how all of this came to be. From time immemorial, we have gazed at the heavens and spun stories about our place among the stars. Today, our tools are telescopes and equations, but the sense of wonder remains as profound as ever. In this journey, we will blend science and poetry, fact and metaphor, as we explore the cosmos on every scale. We will touch on cosmology and physics, astronomy and mathematics, philosophy and human curiosity, all the lenses through which we seek understanding. Together, let us venture to the very beginning of time and back, and to the farthest reaches of space, in pursuit of the story of everything. Our journey begins at the very beginning, at the origin of everything we know, in the primordial darkness, before a single star had ever shone. All that would become the universe was cradled in a point smaller than an atom. It is nearly impossible to imagine. A seed of unimaginable density and heat. A single point that held the potential for galaxies, for life, for every atom and every moment in time. And then, in an instant about 13.8 billion years ago, that seed exploded into growth. There was a flash of pure creation, a moment we call the Big Bang. Time and space themselves were born in that moment. What had been nowhere became everywhere. What had been nothing became everything.
The newborn universe expanded with incomprehensible fury. In a tiny fraction of a second, it swelled from microscopic to cosmic scales. This extraordinary growth spurt, known as cosmic inflation, stretched space like a balloon inflating at faster than light speed. Distances between points grew by an enormous factor, smoothing out any clumps or curves. Inflation explains why the universe today is so uniform and flat on large scales. It was as if any initial wrinkles in space were ironed out by this tremendous expansion. A smooth, seething fireball emerged from that initial burst. Tiny quantum fluctuations, random little flickers of density in that early vacuum, were blown up by inflation into slight variations in the otherwise even spread of matter. These faint imprints would one day guide the formation of galaxies, but for the moment, the infant universe was a hot, dense soup of energy. As inflation settled, the energy driving it transformed into matter and light. The universe was 1 second old. In that first second, space was filled with an intense, blinding glow. Radiation so hot that it would have vaporized anything, though as yet, there was nothing but fundamental particles. Matter and energy were not yet distinct. They flowed together in a plasma, a fluid of raw creation. Protons and neutrons jostled in temperatures of billions of degrees. In the minutes that followed, the entire universe itself became a nuclear reactor. These building blocks began to combine in countless tiny nuclear forges across the young cosmos. Protons fused with protons, neutrons linked with protons. By 5 minutes of cosmic time, the first atomic nuclei had formed. The simplest elements came into being: hydrogen, the lightest of all, and helium, its slightly heavier kin. A trace of lithium also appeared. In that brief early epoch of nucleosynthesis, the universe forged the basic chemical foundation it would use to build everything else. About 3/4 became hydrogen and 1/4 helium by mass, an elemental newborn universe. Still, no atoms as we know them could yet exist. The universe was far too hot for electrons to settle into orbits around nuclei. Instead, electrons careened freely through the dense plasma, scattering light incessantly. Photons, the particles of light, were trapped in a cosmic fog, bouncing from one free electron to another. Space glowed as bright as the interior of a star, but no light could travel far. The universe was opaque, a brilliant radiance suffused within a swirling, glowing mist. As seconds turned to minutes, minutes to hours, and hours to years, the young cosmos continued to swell and cool. Hundreds of thousands of years passed. Expansion took its toll on the fireball, diluting and cooling it steadily. At around 380,000 years after the Big Bang, a critical threshold was crossed. The temperature fell enough that electrons could finally be captured by nuclei. Protons clutched electrons to form hydrogen atoms. Helium nuclei gathered electrons to become helium gas. This transition is called recombination, though it was the first time such combination had occurred. With electrons now bound into atoms, the fog lifted. The once captive light was free at last. In every direction, a brilliant afterglow burst forth and raced away through space. The universe that had been opaque became transparent. That first light still surrounds us today. It has cooled to a gentle microwave glow that bathes the entire sky. The cosmic microwave background, the oldest light we can see. Back then, it was a searing, orange-white illumination everywhere. As space expanded and cooled, that light's wavelength stretched beyond red, through infrared, and into the microwave part of the spectrum we detect today. Discovered as a faint hiss in radio antennas, this afterglow is a whisper from the time the universe took its first breath as a transparent cosmos. The universe then entered a deep, dark age. With the primal light released and streaming onward, space itself went dark. There were not yet any new sources of light. The primordial gases, mostly hydrogen and helium, now drifted through expanding space like a vast, invisible fog. Gravity, the great sculptor, began to gently tug on the ever-so-slight variations in density left by inflation. Regions that were just a bit denser than average exerted a stronger pull, drawing in matter from their surroundings. Invisible threads of gravity started weaving patterns in the darkness. Over tens of millions of years, those threads pulled gas into clumps. The silent clouds grew denser and tighter until, at last, there was fire again. Perhaps 100 million years after the Big Bang, the first stars were born. Deep in massive collapsing clouds of hydrogen and helium, the pressure and heat ignited nuclear fusion. Starlight pierced the darkness. These first stars were giants, short-lived behemoths burning hot and blue, forging heavier elements in their cores as they shone. They lived for only a few million years before dying in titanic supernova explosions, seeding the surrounding space with the new elements they had cooked up: carbon, oxygen, nitrogen, iron. Ingredients that one day would be essential for planets and life. The death of each star sent enrichment into space, and out of the ashes, new generations of stars would eventually form. Their brilliant ultraviolet light also gradually burned off the primordial hydrogen fog in intergalactic space, rayonizing the cosmos and allowing light to travel freely everywhere. With the birth of stars, the cosmos had begun to light up structure by structure, ending the long night of the Dark Ages. The cosmic dawn gave way to a growing day as the first stars and nascent galaxies illuminated the heavens. As stars gathered, they formed the first proto-galaxies, small galactic building blocks that later merged into larger ones. Gravity continued its tireless work on grander scales. Stars bound themselves into galaxies, and galaxies gravitated into clusters. Over hundreds of millions, and then billions of years, a vast cosmic web took shape. Galaxies pulled on one another along filaments of invisible matter, collecting into chains and sheets. Imagine a spider's web made not of silk but of galaxies, strung along invisible filaments, with enormous voids of near-empty space in between. Astronomers mapping millions of galaxies, for instance in the Sloan Digital Sky Survey, have unveiled this vast cosmic web in detail, huge filaments like the Sloan Great Wall stretching across hundreds of millions of light-years, and immense voids nearly empty of galaxies. It serves as the large-scale structure of the universe. Galaxies grouped like sparkling dew on cosmic threads, clusters at their intersections, and between them, great dark gaps where few galaxies shine. Interestingly, researchers have even drawn analogies between the cosmic web and biological systems. One experiment showed that a slime mold, when presented with simulated galaxy clusters as nutrient sources, grew tendrils that closely traced the filaments of the cosmic web, as if nature repeats patterns on vastly different scales. From a vantage point far away, the universe would look foamy or spongy, matter gathered into fibrous clusters surrounding empty cavities. And within each galaxy, countless stars swirled, orbiting their galactic centers like bees around a hive. What about the universe as a whole? Is it shaped like a sphere, a saddle, a donut, or an infinite flat expanse? As far as we can discern, space on the largest scales is remarkably flat, like an endless plane. If you set off in a straight line among the galaxies, you would not curve back around to where you started, at least not within any distance we can observe. The cosmos could extend forever, infinite in extent. It might also be finite yet unbounded, curving back on itself only on scales beyond our observational reach, rather like the surface of a balloon is finite, yet has no edge. Current measurements of cosmic geometry show no significant curvature. To the best of our knowledge, parallel beams of light travel straight and never meet. It is currently unknown whether the universe might eventually loop back in some topologically complex way, like a 3D torus. But if it does so on a scale far larger than the observable horizon. In all directions, space stretches out similarly, giving us no hint of an edge or a boundary. We are, however, limited in what we can see, not by any solid wall at the universe's edge, but by time itself. The observable universe is a sphere around us, about 46 billion light-years in radius, delineated by the distance light has been able to travel since the Big Bang. We can only see as far as the light that has had time to reach us. Beyond that horizon, light from those regions has not yet arrived, and perhaps never will. Thus, we gaze out at a bubble of the universe around us. Beyond it, the mystery continues, perhaps with more galaxies and more cosmic web stretching indefinitely, or perhaps something radically different. For now, it remains hidden, a tantalizing unknown just out of reach. The cosmic horizon is not only a physical limit, it's also a reminder of our cosmic myopia. It's like standing on the shore of a vast ocean at night. We see the dark waters meet the sky at the horizon and wonder what lies beyond. Our cosmic horizon is such a shore, and though we cannot see past it, we imagine an endless sea beyond. Even as structures formed and stars lit up, the overall expansion of space never halted. The universe kept stretching, carrying galaxies farther apart from each other. The very fabric of space is like an ever-expanding canvas, and the galaxies are like dots of paint on that canvas, drifting away as the canvas grows. The light that travels between galaxies is stretched too. As space expands, wavelengths of light elongate, shifting toward the red end of the spectrum. Thus, when we observe distant galaxies, their light is reddened, a cosmological redshift that encodes their motion through the expanding space. In the early 20th century, astronomers armed with new telescopes made a profound discovery. Nearly all galaxies beyond our local group are racing away from us, and the farther they are, the faster they recede. Edwin Hubble measured this relationship, finding that the speed of recession is proportional to distance. Today, this rate of expansion, known as the Hubble constant, is roughly 70 kilometers per second per megaparsec, meaning a galaxy about 3.3 million light-years away recedes at roughly 70 kilometers, and one twice as far at about 140 kilometers. This linear relationship, now called Hubble's law, was revolutionary evidence that the universe is expanding uniformly in all directions. It is not that we are at the center of an explosion, but rather that space itself is swelling, so every galaxy sees others moving away. Imagine raisins in a rising loaf of bread. Each raisin sees the others receding as the dough between them expands. Just so, our Milky Way and all galaxies are like raisins embedded in the expanding space of the cosmos. Yet even as Hubble and others revealed an expanding universe, other observations soon uncovered a deeper mystery in those galaxies. In the later 20th century, astronomers like Vera Rubin noticed that stars at the outskirts of spiral galaxies were orbiting their galactic centers at startling speeds, too fast to be explained by the gravity of the visible stars and gas alone. According to Newtonian physics, those outer stars should have been flung off into space, or conversely, one would need far more mass in the galaxy to hold them in their orbits. Something unseen, some additional gravitating mass, was providing the extra pull. Similarly, clusters of galaxies were found to contain far more gravity than the visible matter could supply. It was as if an invisible halo of mass surrounded clusters and individual galaxies alike. This mystery substance was dubbed dark matter. It does not shine or interact with light, making it invisible and detectable only through its gravity. But it is abundant, far more abundant than the ordinary matter we see. Roughly 85% of the matter in the universe is dark matter, about 5 times more mass than in normal atoms. It acts as the scaffolding of the cosmic web. It clumps under gravity, forming massive halos, and ordinary gas falls into those halos to form galaxies. Without dark matter's guiding hand, the universe would lack much of the structure we observe. Galaxies might not have had enough gravitational glue to coalesce as they did. We even observe gravitational lensing, light from distant objects bending around invisible mass, revealing dark matter's presence. In colliding galaxy clusters like the Bullet cluster, the normal matter, hot gas visible in X-rays, can be seen to separate from where most of the gravity is. The gravitational center follows the unseen dark matter, providing direct evidence of this hidden mass. We still do not know what dark matter is. Perhaps some as yet undiscovered elementary particle that interacts only weakly with normal matter, often hypothesized as WIMPs or axions, or something more exotic like primordial black holes or a modification of gravity itself. Experiments deep underground and in particle accelerators are attempting to detect dark matter particles directly, so far without success. For now, we infer dark matter's presence by how it holds galaxies together and how it tugs on light passing by. It is the universe's invisible skeleton, a shadowy scaffolding that shaped the beautiful pattern of galaxies and clusters, all while remaining hidden from our eyes. As if dark matter were not mysterious enough, an even stranger ingredient dominates even that. For a long time, scientists assumed that the expansion of the universe, while continuing, should be slowing down over time. After all, gravity pulls all matter together. The collective gravity of galaxies, dark matter, gas and stars should gradually tug at the expansion, perhaps even causing it to reverse in the far future. But in 1998, 2 teams of astronomers observing distant type Ia supernovae, exploding stars used as standard candles, made a shocking discovery. The supernovae were dimmer and farther away than expected, indicating that the expansion of the universe was not slowing at all. It was speeding up. Over the last few billion years, the galaxies have been accelerating away from each other. Some kind of force or energy inherent to space is pushing them apart. Decades earlier, Albert Einstein had introduced a cosmological constant into his equations of general relativity to allow for a static universe, not realizing the universe actually expands. When Hubble's expansion came to light, Einstein reportedly called that constant his greatest blunder. But now, the accelerating cosmos implies something like Einstein's constant truly exists after all. We call this phenomenon dark energy, a name that signifies how little we truly understand it. Dark energy appears to be a property of space itself. Every cubic centimeter of vacuum seems to carry a minuscule amount of energy that, summed over billions of light years of emptiness, dominates the universe. Today, roughly 68% of the universe's total energy content is this dark energy, with about 27% dark matter and only 5% normal matter composing the rest. It behaves almost like an anti-gravity, driving galaxies apart on large scales and overpowering the attractive force of gravity at cosmological distances. Perhaps dark energy is a fixed property of the vacuum, a realization of Einstein's cosmological constant, or perhaps it changes over time, a dynamic field dubbed quintessence. Upcoming observatories and surveys are dedicated to measuring the expansion history more precisely, in hopes of discerning the true nature of this mysterious energy. For now, dark energy remains an enigma at the heart of cosmology, a gentle but inexorable push woven into the fabric of space-time. What does an accelerating expansion mean for the future? The fate of the universe hinges on dark energy's nature. If dark energy remains constant, a steady push that continues indefinitely, then the expansion will not only continue, but accelerate forever. Galaxies that are not gravitationally bound to us will recede faster and faster, eventually zooming away at such speeds that their light can no longer reach us. In tens of billions of years, distant galaxies will disappear beyond our horizon, leaving only the gravity-bound local group of galaxies, by then likely merged into one large galaxy, visible. If we look far, we'll see darkness where once galaxies twinkled. Over extremely long timescales, the stars within our remaining galaxy, or merged Milk-Dromedar galaxy, will age and die. New stars will form more slowly as the available gas becomes sparse. Trillions of years from now, the last stars will exhaust their fuel and flicker out one by one, leaving a universe populated only by faint stellar remnants, white dwarfs cooling to black, neutron stars, and black holes. The cosmos will grow colder and darker as eons pass. Eventually, even black holes will evaporate via Hawking radiation, on timescales so vast, 100 years or more, that they defy imagination. What remains will be a thin haze of fundamental particles and energy, spread so dilute that for any given volume of space, on average, there might be essentially nothing in it. This is the Big Freeze or heat death scenario, a universe that expands forever while cooling asymptotically toward absolute zero, approaching a state of maximum entropy where no organized energy remains to do work. If an astronomer were alive in that far future of a Big Freeze, they would see a very different sky. Beyond our small gravitational neighborhood, no galaxies would be visible at all, only an endless black void punctuated by the occasional faint glow of a red dwarf or the spark of a distant supernova, becoming rarer with time. The evidence of the Big Bang itself would fade. The cosmic microwave background, which today is a cool 2.7 K glow, would be stretched to radio waves so long and weak as to be undetectable. The chemical elements would slowly transmute as protons perhaps decay over immensely long times, if proton decay is a real phenomenon. Eventually, it would be a universe of scattered particles and low-energy photons, drifting in an ever-growing silent darkness. Time would continue, but virtually nothing of interest would happen. It is a state as close to true cosmic stillness as can be. The universe would have effectively died, not with a bang, but with a long, drawn-out whimper. There are even more violent speculative possibilities. If dark energy is not constant but instead grows stronger with time, imagine a form of phantom energy, then the acceleration would steepen catastrophically in the far future. In such a scenario, the repulsive effect of dark energy could increase without bound. One could imagine the final moments of such a universe. Galaxies rush away from each other at ever-increasing speeds. Eventually, in the distant future, the expansion's pull becomes so strong that it overcomes the gravity holding galaxies together. First, galaxy clusters are pried apart. Later, the galaxies themselves begin to fly apart as their stars disperse into the expanding void. Then solar systems destabilize, planets drift away from their stars. As the end approaches, even stars and planets themselves would be torn apart, and then molecules and atoms. In the last fractions of a second, the tidal forces of expansion would become essentially infinite, shredding the very subatomic particles. This hypothetical final calamity is called the Big Rip. It would be a universe ending in a kind of ever-accelerating explosion, where every bond, gravitational, electromagnetic, even nuclear, is overcome by the expansion of space. One moment, you might have galaxies. Moments later, only individual atoms. Finally, nothing at all but a thin, featureless energy as space rips itself apart. It's a highly speculative scenario. Current data do not favor such extreme dark energy behavior, but it serves to illustrate the dramatic ways our universe's story could conclude under different rules. On the other hand, what if dark energy were to weaken over time or even reverse sign? Or what if the universe had contained so much matter that gravity could eventually overwhelm expansion? In those cases, the expansion might slow down, stop, and ultimately reverse. Distant galaxies that are now receding would one day halt and begin to come closer again. This is the Big Crunch scenario, the opposite of the Big Bang. In a universe headed for a big crunch, observers in the far future might see the expansion first slow to a crawl. Distant galaxies that once sped away would linger at the edge of visibility. Then, gradually, they would start to approach, their light shifting from red back to blue. The cosmos would begin to shrink. Over billions of years, separated clusters of galaxies would converge. Previously unreachable galaxies would become visible again as they rush inward. The cosmic microwave background temperature, which had been dropping, would begin to rise as the universe contracts and heats up. Eventually, the night sky would no longer be dark, but aglow, first dotted with an increasing number of bright galaxies coming together, then suffused with the glow of a background fire as intergalactic gas is compressed and reheated. In the final epoch, the entire sky might blaze like the surface of a star, white hot, as galaxies merge into a single, incandescent mass. Finally, all matter and energy would crash together in an ultra-dense state, perhaps a mirror image of the Big Bang. Some have imagined that such a collapse could bounce, an implosion leading to a new explosion, a Big Bang after the Big Crunch, giving birth to a new universe. This Big Bounce idea suggests a cyclic cosmos without beginning or end, eternally reborn. However, given what we observe, particularly the presence of dark energy, a Big Crunch seems very unlikely for our universe. The balance of evidence indicates that we are headed toward eternal expansion, either the Big Freeze or Big Rip, with Big Freeze considered far more plausible under current data. Nevertheless, thinking about these scenarios reminds us that our universe's story might have multiple chapters, and perhaps even an epilogue beyond our own cosmos. As we ponder the fate and origin of our universe, we naturally wonder, is our universe the only one, or is it just one bubble in a vast frothing sea of universes? Modern theories in cosmology and physics have opened the door to the idea of a multiverse, the possibility that our universe is not alone, but part of a far larger system of universes. The existence of dark energy and the precise balance of physical constants in our universe have led some to wonder if our cosmos is just one of many, its properties one random draw among myriad universes. In a multiverse, what we call fine-tuned constants of nature, like the strength of gravity or the charge of the electron, might vary from one universe to another. We find ourselves in one that permits galaxies and life simply because those that don't would be sterile and uninhabited, with no observers to notice them. One compelling multiverse idea arises from the theory of eternal inflation, a variant of the inflationary scenario we discussed earlier. In eternal inflation, the rapid expansion of space didn't end everywhere at once. While inflation stopped in our region, allowing particles and galaxies to form, other regions of space might still be inflating, or might have ended their inflation at different times, each giving rise to its own bubble universe. Our universe, then, would be one such bubble among countless others, expanding within a larger inflating space-time. Each bubble could have its own distinct laws or constants. Some might be barren, with no matter, or with physics hostile to complexity. Others might be roughly similar to ours. Perhaps others are wildly different with more dimensions or different fundamental forces. We cannot directly see these other bubble universes because they would lie beyond our cosmic horizon and indeed beyond any space-time connection with us. But they are a natural extrapolation of inflation theory. These other universes could be as real as our own, each constituting its own reality bubble. The multiverse concept comes in different flavors. The level 1 multiverse essentially says that if space is infinite and uniformly filled with matter, then far beyond our observable horizon, there could be regions identical to ours, or slightly different, or vastly different, simply by random chance arrangements of matter. In an infinite universe, every possible configuration of particles, every possible history, would occur somewhere. Our observable universe would be just one patch of an infinitely vast quilt. The Level 2 multiverse corresponds to the eternal inflation scenario, bubble universes. Each bubble might have different physical constants or particle types, because the process of symmetry breaking in physics could end up differently in each one. One bubble might have a stronger electromagnetic force. Another might have a neutron a bit heavier, preventing stars from working. We find ourselves in a bubble that is congenial to complexity, because only such bubbles can produce observers. Another intriguing idea is the Level 3 multiverse, which arises from quantum mechanics, the many worlds interpretation. In quantum theory, every event that has multiple possible outcomes, like a particle decaying or not decaying, is sometimes thought of as splitting reality into multiple branches. According to this interpretation, all possible outcomes actually occur, each in its own branch of the wave function of the universe. So in one quantum branch, universe, the cat is alive. In another, it is dead, to invoke the famous Schrödinger's cat thought experiment. These parallel universes are usually thought to be non-communicating, existing in a superposed mathematical state, rather than separate inflating bubbles. But some argue they are just as real as our own. In effect, this would mean that with every quantum event, the universe, at least at the level of quantum information, splits into multiple histories, creating an ever-branching tree of parallel realities. If true, the number of universes would be mind-bogglingly large and constantly increasing. There is even a conjectured Level 4 multiverse, the ultimate ensemble, which posits that all universes that can be described by consistent mathematical structures exist in some sense. In this view, mathematics and reality are one and the same. Any self-consistent set of physical laws, any mathematical model, corresponds to an actual universe somewhere. This is a philosophical speculation more than a scientific theory, but it underscores how far the multiverse idea can be taken. So, could it be that what we call everything, our observable cosmos, is but a drop in a much grander ocean of existence? It's possible. At present, the multiverse remains a theoretical idea. We have no direct evidence of other universes, and some argue we never could, by definition. Yet the concept finds footing in serious science because it can arise naturally from models like inflation, and because it offers answers to questions like why our universe has the properties it does. They might be random picks from a larger distribution. If the multiverse is real, then the totality of existence is even grander than the universe we've been discussing. It means there could be countless other Big Bangs, countless other expansions, perhaps countless other versions of you and me, or perhaps realities utterly without analogy to anything we know. It is a speculative, almost metaphysical extension of our theories, one that reminds us that as vast as the universe is, there could be more, much more, beyond it. No matter how many universes exist, we know that we can only directly explore our own, and it has plenty of mystery to keep us occupied. One such mystery is deeply connected to our everyday experience, the nature of time. Time flows ever forward, carrying us from moment to moment. We remember the past and anticipate the future, but we never experience events in reverse. This one-way direction of time, from past to future, is called the arrow of time. Why does time have an arrow? The answer, as far as physics can tell, lies in entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy tends to increase or, at best, stay the same. It never decreases spontaneously. This law gives a direction to processes. Things go from ordered to disordered, not the other way around. An egg breaks and scrambles, but a scrambled egg does not unbreak itself into a whole egg. A drop of ink disperses in water, but the ink won't gather back into a concentrated drop on its own. These processes are not forbidden by any fundamental microscopic law. Newton's and Schrödinger's equations work the same forward and backward in time, but they are overwhelmingly unlikely to happen in reverse, because that would require a decrease in entropy. The arrow of time in our universe is fundamentally linked to the initial conditions of the cosmos. The universe began in an extraordinarily low entropy state. This might sound strange because the early universe was a hot, dense plasma which seems very disordered, but in fact, it was extremely uniform and simple, free of complex structures, making its entropy lower than it could have been. It's as if all the matter and energy were evenly spread out and gravitationally unclustered, a very ordered configuration compared to what could be. Because the universe started with such low entropy, there was essentially nowhere to go but toward higher entropy. As the universe expanded and cooled, entropy increased, gradients smoothed out, structures formed even as overall disorder grew. For example, the formation of stars and galaxies increases local order, but overall entropy still rises due to the production of lots of waste heat and the gravitational settling that releases energy. The arrow of time is a manifestation of this rise of entropy. We perceive time flowing forward because that is the direction of increasing entropy. If you were to film a glass shattering and play it backwards, you'd see entropy decreasing and immediately intuit that time is reversed in the film. In the real universe, we do not see such things. One might ask, why was the entropy of the early universe so low to begin with? This remains one of the deep, unanswered questions in cosmology. Some suggest it might be a boundary condition of our universe, perhaps set by a prior state or by the laws of quantum gravity. Others propose that if there are multiple universes or cycles, we naturally find ourselves in one that started in a low entropy state, because only such a universe can develop the complexity needed for observers. Regardless, that low entropy beginning is what allowed an arrow of time to emerge. From it flowed the entire history of structure and complexity. Stars shine, increasing entropy by radiating heat. Life grows and metabolizes, increasing entropy in surroundings even as it creates local order. And eventually stars die and things run down. If we project trillions upon trillions of years forward, in the heat-death scenario, entropy will near a maximum. The arrow of time will effectively fade, not because time has reversed, but because almost nothing changes anymore. There are no organized processes left to distinguish a forward direction. In the far, far future of a big freeze, the universe might reach a state of near equilibrium where, without gradients or differences, the concept of before and after loses much of its meaning. Time and entropy tie together the grand cosmic and the intimate personal. The increase of entropy sets the thermodynamic arrow that makes memory possible. We remember lower entropy past states. It is why we grow older and not younger. It's the reason we can't unmix cream from coffee or unburn a piece of paper. It's fascinating that this everyday irreversibility is rooted in the initial conditions of the entire universe. We've journeyed from the enormous clusters of galaxies to the minute atoms and particles, but we haven't yet delved into the truly fundamental fabric underlying reality, the quantum realm. On the smallest scales, the world behaves in ways that defy our classical intuitions. In the quantum realm, particles are also waves, and everything is described by a fuzzy haze of probabilities rather than definite certainties. Take an electron. In an atom or in transit, it doesn't have a single precise location. Rather, it exists as a cloud of probability, a smeared-out wave of potential positions. Only when we interact with it, measure it, does the electron seem to choose a location or state. This is the bizarre phenomenon of wave function collapse, in interpretations where collapse is a thing. Before observation, Schrödinger's cat is both alive and dead in a quantum sense. Before measurement, the electron has many possible positions. For example, if we shoot electrons at a screen through two narrow slits, something astonishing happens. The electrons, one by one, form an interference pattern on the detection screen, alternating bands as if they were waves that passed through both slits and interfered with themselves. This happens even if we fire them one at a time. It's as though each electron goes through both slits as a spread-out wave. However, if we set up a detector to observe which slit the electron actually goes through, trying to catch it in the act and force it to be a particle going through one path, the interference pattern disappears. Now the electrons behave like little bullets, going through one slit or the other, and no interference fringes form, just two piles behind the slits. The mere act of observation changes the outcome at the quantum level. It's as if nature allows the electron to explore many possibilities, wave behavior, until we insist on knowing which one happened, at which point nature chooses and the wave of possibility collapses into a single result. Empty space itself is not truly empty in the quantum sense. Even in a perfect vacuum, quantum fields are continuously fluctuating. Particle-antiparticle pairs momentarily pop into existence and then annihilate so quickly and so spontaneously that we can barely infer their presence. They leave subtle effects on energy levels and forces. These quantum fluctuations are not just theoretical quirks, they had cosmic consequences. During inflation, those tiny fluctuations in density and energy were stretched out to macroscopic scales. Regions that were ever so slightly more dense or less dense than others became the seeds for all large-scale structure. The spots in the cosmic microwave background that are a bit warmer or cooler, denser or less dense, trace back to these quantum wiggles. It is a breathtaking linkage. The reason galaxies exist where they do is partly because of random subatomic jitter in the universe's earliest moments. The entire cosmic web is essentially amplified quantum noise. Quantum physics underpins nearly everything in our daily experience, even though we don't notice its strangeness on large scales. The atoms in our bodies are held together by electron wave functions and quantum bonds. The sun shines because quantum tunneling allows protons to overcome their electrostatic repulsion and fuse into helium. Without quantum tunneling, the sun's core wouldn't ignite as easily. Computers and modern technology rely on quantum mechanics, semiconductors, lasers. In a sense, the solidity of a rock, the behavior of a chemical reaction, the colors of the rainbow, all trace back to quantum rules. We live in a quantum universe, though its oddness becomes apparent only when we look at small scales or specific conditions. There is also the deep mystery of quantum measurement and reality. Does the wave function collapse when observed? Does the universe split into branches for each outcome, the many worlds idea? No one knows for sure which interpretation of quantum mechanics is correct, or if there's a deeper theory that will resolve these questions. What we do know is that quantum mechanics is astoundingly successful in predicting outcomes. It has been tested to high precision. Reality, at its foundation, is governed by probability waves and uncertainty. It's almost as if nature, at a fundamental level, decides events by a kind of controlled randomness within strict statistical rules. Our voyage has taken us from the beginning of time to the structure of space, from the largest assemblies of galaxies to the subatomic flickers of the vacuum. Along the way, we encountered phenomena that are poetic in their grandeur and scientific in their detail. An afterglow from creation itself still shining to us, invisible matter holding galaxies in its gravitational embrace, a mysterious energy pulling the cosmos apart, and quantum whispers setting the stage for galaxies. Let's return for a moment to that ancient light we freed at Recombination, the cosmic microwave background, CMB. After traveling for 13.8 billion years, it reaches Earth as a faint, cold glow in all directions, a few photons per cubic centimeter. In 1965, two engineers, Arno Penzias and Robert Wilson,
were using a big horn antenna in New Jersey, trying to eliminate all sources of noise from their radio measurements. They kept encountering a persistent hiss, uniform across the sky, day and night. At first, they thought it might be due to urban interference, or pigeon droppings in their antenna, or instrument malfunction. But none of those explained it. Meanwhile, a group of physicists at Princeton, Dicker, Peebles, et al., had been looking for exactly such a signal. The predicted relic radiation from the hot early universe, which years earlier, scientists like George Gamow had calculated should by now be just a few degrees above absolute zero. Penzias and Wilson had stumbled upon the very signal that those theorists were seeking. It was soon confirmed that this microwave hiss came from all directions uniformly and had a blackbody spectrum of about 2.7 Kelvin, just what the Big Bang model predicted. The cosmic microwave background was the long-predicted afterglow from the hot young universe, now cooled to a whisper. When we map the CMB across the sky, as satellites like COBE in 1989, WMAP in the 2000s, and Planck in 2013 have done with increasing precision, we find it is almost the same in every direction, extremely uniform to about 1 part in 100,000. It's as if the entire sky were painted with one color of incredible smoothness, with only the faintest speckles. Those speckles, the tiny temperature anisotropies, carry a wealth of information. They are the imprints of the primordial sound waves and density ripples in the early universe. The pattern of spots tells us the universe's age, composition, and geometry. By carefully analyzing the CMB, scientists have confirmed the age of the universe, how 13.8 billion years, determined that space is flat to within a tiny margin of error, and measured the ratios of normal matter, and dark energy that we mentioned. The CMB is like a baby picture of the universe, taken when it was only 380,000 years old. In that baby picture, we can already see the slight non-uniformities that eventually grew into clusters of galaxies. It's astonishing that we can observe this. When you tune an old television between channels and see static, a small fraction of that static is actually CMB photons, literally relics from the Big Bang hitting your TV's antenna. The CMB also provides evidence that ties together many threads of our story. It confirms the Big Bang. A static universe would not have such a background. It supports inflation. The uniformity and specific patterns match inflationary predictions. And it informs the dark matter models. The CMB pattern is sensitive to the amount of invisible mass. It is a Rosetta Stone for cosmology, decoded through careful, rigorous science. And yet, when one simply gazes at the visualizations of the CMB, with its gentle swirls of red and blue, indicating tiny temperature fluctuations, one can't help but feel a sense of wonder. This mottled oval image, often shown in textbooks and documentaries, is the imprint of the primordial cosmos on the sky, the oldest light we will ever see, a light that has traveled for almost the entire history of the universe to reach us. Within this vast cosmic unfolding, on at least one small planet, the expansion and cooling of the universe eventually led to something new, life and consciousness. The atoms forged in stars and scattered by supernovae became the raw material for new star systems. About 4.6 billion years ago, one particular cloud of gas and dust, already enriched by previous generations of stars, collapsed to form our Sun and its family of planets. The third planet from this sun had the right conditions for a remarkable chemistry. In its early oceans and coastal environments, a rich molecular broth swirled. On this young Earth, a complex chemistry brewed in warm ponds, in tidal pools, and around underwater hydrothermal vents. Complex molecules formed in the warm, wet cradles, perhaps sparked by lightning in the atmosphere or by geothermal energy in the crust. Perhaps in sunlit shallow pools, left to evaporate on volcanic shores, or in the mineral-rich hot springs on the ocean floor. Simple chemistry crossed the threshold to self-replication. At some point, simple self-copying molecules emerged. This was the origin of life, around 4 billion years ago.
From those humble beginnings of primitive microbes, life evolved in complexity and diversity, shaped by mutation, competition, and time. Tiny cells coalesced into more complex cells, which eventually formed multicellular colonies. By around 540 million years ago, the Cambrian explosion filled the seas with an astonishing variety of creatures. Life took hold on land. Plants and fungi colonized the continents, followed by insects and amphibians, then reptiles and dinosaurs. Each living organism was, and is, a little chemical machine, drawing energy from the environment to maintain its internal order, a local reversal of entropy paid for by increasing entropy in its surroundings. In this way, life is a kind of cosmic rebellion against the trend toward disorder, though only a temporary and localized one. Through life, the universe explored an entirely new realm of complexity. After dinosaurs were wiped out 66 million years ago by an asteroid and other factors, mammals rose to prominence. Some primates in Africa, a few million years ago, left the trees for the savanna. They grew bipedal and clever. They made tools and learned to cooperate in groups. By about 300,000 years ago, anatomically modern humans had appeared. With the emergence of Homo sapiens, the universe began to be aware of itself in an unprecedented way. We gazed at the stars with curiosity and imagination. Over thousands of years, we developed language, culture, mythologies about the cosmos. We harnessed fire, energy for entropy consumption. We built shelters. We eventually tilled fields and founded cities. We looked up and saw patterns in the sky, crafting constellations and calendars. Human curiosity pushed us to ask not just how to survive, but why we are here, what the stars are, what the sun is, and how it all began. Fast forward to the modern era. In just the past few centuries, we have, through the scientific method, unraveled many cosmic mysteries. We discovered that those points of light in the night sky are other suns, and some of those suns host planets of their own. We've confirmed thousands of exoplanets and infer that the galaxy holds billions more. We found that our sun is just one star among hundreds of billions in the spiral galaxy we call the Milky Way, and that our galaxy is just one of trillions in the observable universe. We've begun to understand the forces and particles that govern nature. We've peered back in time with powerful telescopes to see galaxies in their infancy, and we've peered into the atom to unlock the secrets of quantum physics. Life, at least here, evolved to consciousness that can contemplate the universe. That is a profoundly poetic fact. We are made of dead stars, and those very ashes have somehow become alive and able to wonder about their origins. The universe spent billions of years evolving us, and through our eyes, it now sees itself. We are a way for the cosmos to know itself, Carl Sagan famously said, encapsulating this truth. Our self-awareness makes the universe not only a physical phenomenon, but also an experience. Through our literature, art, and science, the cosmos has gained the ability to reflect upon itself, to study its own laws, to admire its own beauty. Are we alone in this astounding capability? Perhaps not. The universe is so vast that it seems improbable that Earth would be the only cradle of life. Perhaps in some warm pond on an exoplanet under a distant sun, chemistry has given rise to biology. Perhaps on a moon orbiting a gas giant, beneath an icy crust, alien microbes flourish near thermal vents. Maybe on some planet in the habitable zone of another galaxy, intelligent creatures build their own tools and look up at their sky with questions. As of now, we don't have evidence of life beyond Earth, but the possibility stirs our imagination. Whether life is common or exceedingly rare, the fact remains that life here has transformed a part of the cosmos into something self-aware. And so here we find ourselves, clever, self-aware creatures built of cosmic dust, living on a minor planet, orbiting an ordinary star in a typical galaxy, yet able to contemplate the entirety of existence. Our physical insignificance is undeniable. We are infinitesimal,
compared to the breadth of the cosmos. Our entire world is just a tiny mote of dust in a cosmic ocean, a pale blue dot adrift among countless stars. But our ability to understand and appreciate the cosmos gives us a significance of a different kind. We might be rare, perhaps the only intelligent beings for parsecs around, or maybe one of only a few in our galaxy. Maybe life teems in the universe, or maybe it is exceedingly scarce. Either way, in our corner of space and time, we are the only known eyes and minds observing the grand cosmic drama. Through us, the universe has become aware of itself. Through our scientific instruments, the universe maps its own structure. Through our poetry and art, the universe speaks of its own majesty. There is something profoundly meaningful about this, even if one views it in a purely secular, scientific way. The cosmos has given rise to beings who can know the cosmos. We have inherited the fiery hearts of ancient stars in the iron of our blood, the calcium of exploded supernovae in our bones, and the carbon and oxygen from countless stellar furnaces in every organic molecule of our bodies. We are literally children of the stars, made of stardust. And those children can now, like grown progeny, look back and study their parents, the stars, and grandparents, the galaxies, the Big Bang. This unity of origins gives us a connection to everything. We are not separate from the universe. We are portions of it, inextricably linked. The laws of physics that formed a galaxy also form the neurons in our brain that fire when we gaze at a galaxy. With knowledge, however, comes the humbling realization of how much we don't know. Our journey through cosmology answers many questions, but raises others. Why is there something rather than nothing? Did time begin with the Big Bang, or is there a multiverse with different realms beyond ours? What is the true nature of space and time on the smallest scales? Are they quantized into discrete bits, as some theories like quantum gravity suggest? We don't yet have a fully unified theory of quantum mechanics and gravity. Thus, the exact first moments of the Big Bang, the Planck time, and what happened before inflation remain mysterious. We still do not know what dark matter is, despite it making up most of the matter in the universe. We still do not know why an early hyperinflation happened, or if it's even the final answer to the early universe's smoothness and flatness. We aren't sure if dark energy is truly constant or has subtle variations, and the nature of dark energy, why vacuum has the energy it does, is deeply perplexing. In fact, theoretical physics calculations of vacuum energy overshoot observations by an outrageous factor, a major puzzle. We do not know if life is a common cosmic phenomenon, or an extremely lucky fluke confined to Earth. We have not yet detected signals from other civilizations, though projects like SETI are listening. We do not know the fate of humanity, whether we will spread to the stars or remain bound to our lovely, pale blue dot. In short, we still float on a sea of mystery, with islands of knowledge gained so far. Standing at this precipice of knowledge and mystery, one cannot help but feel a profound awe. The universe is ancient and vast beyond comprehension, yet here we are, small creatures with curious minds, capable of tracing its story from the primal fireball to the present, and even forecasting its possible futures. That story, from the simplicity of the early fireball to the complexity of a living world, is both humbling and inspiring. The cosmos is breathtaking, not just in scale, but in the way it has produced patterns and coherences. The periodic table of elements forged in stars, the spiral patterns of galaxies, the double helix patterns of DNA that allowed creatures like us to emerge. There is a deep harmony in how the same physical laws apply across all scales. The nuclear reactions blazing in the core of a distant star obey the same physics as the glow of your reading lamp. The gravity that makes a planet orbit the sun is the same gravity that makes galaxies dance around one another in clusters. Mathematics, abstract patterns of logic, proves to be an incredibly effective language to describe these laws, suggesting a wondrous connection between the human mind and the workings of the universe. It's as if the universe has a hidden symmetry or order that we can glimpse through mathematics and science. Our journey of understanding is far from over. Each new discovery in astronomy or physics tends to open new questions. When we discovered the expansion of the universe, we were led to ask about the beginning, Big Bang, and the ultimate fate. When we found the cosmic microwave background, we were led to the idea of inflation. When we observed unexpected galaxy rotations, we hypothesized dark matter. When we measured distant supernovae, we stumbled upon dark energy. Every time we peel back a layer of reality, there is another layer waiting, sometimes with stranger questions. This is the beauty of science and exploration, a continuous unfolding story, each chapter building on the last, but the book seemingly without end. Picture the cosmic timeline as a grand narrative, a story that begins with nearly featureless energy and evolves into intricate worlds and beings. It's a story that spans 13.8 billion years and perhaps will span trillions more. To grasp our place in this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. By early February, the first stars ignite. By mid-March, galaxies are forming. The Milky Way might form around May. Our Sun and Earth appear roughly in early September on this cosmic calendar. Life arises on Earth by late September. Complex multicellular life proliferates in November. Dinosaurs roam the Earth on December 25th, Christmas Day, and go extinct on December 30th. Modern humans emerge only in the final hour of New Year's Eve, and all of recorded human history flashes by in the last seconds before midnight. In those final seconds, we develop agriculture, build the pyramids, invent the telescope, land on the moon, and contemplate the Big Bang. When the clock strikes midnight to herald a new cosmic year, perhaps that represents some distant future state we've yet to comprehend. This cosmic calendar shows just how young we are. Human civilization is an eye blink in cosmic time, and even the Earth is a relatively late chapter in the story. We arrived at the tail end of the year, so to speak, but armed with curiosity and intellect, we busied ourselves in those last seconds learning about all that came in the months before us. Now we, ephemeral yet mindful, look to the future. We wonder what's next for the universe and what's next for us. Barring extraordinary intervention, the universe will continue to expand and evolve according to the physical processes we have discussed. As for humanity, we too are subject to cosmic forces, but have some say in our destiny if we are wise. We may spread to other planets, carrying our legacy of curiosity with us beyond Earth, ensuring that life and consciousness have a longer future than our single planet's fate. We may find ways to harness new energy sources or manipulate space-time, ideas once in the realm of science fiction, but who knows what knowledge awaits in the coming millennia. Or we may struggle and someday perish, becoming a brief spark that faded out. But even if our particular lineage ends, perhaps other intelligences elsewhere will carry on, or new intelligences might evolve from what we leave behind, intelligent machines, or new species. The desire to know and to wonder might itself be as resilient as life. From the standpoint of the universe, meaning is not something handed down from the stars. It is something we create. We infuse the cosmos with meaning by contemplating it. A galaxy 100 million light-years away has no idea of its grandeur, but we know, and in knowing and seeing beauty in it, we give it meaning, at least to us. In a way, the cold equations of physics blossomed into the warmth of human experience and inquiry. The universe is often described as a cold, uncaring place, and physically it is vast and mostly inhospitable. But through us, it cares about itself, in the sense that we care and we are part of the universe. This connection may be philosophically subtle, but it is emotionally powerful. Our exploration is ongoing. Even now, new telescopes like the James Webb Space Telescope peer into the distant past,
seeing galaxies forming just a few 100 million years after the Big Bang, giving us new data points in the cosmic saga. Particle accelerators, like the Large Hadron Collider, probe higher energies, trying to recreate conditions just after the Big Bang, searching for clues of new physics, perhaps particles that could explain dark matter or hints of extra dimensions. Experiments in deep mines attempt to catch a glimpse of dark matter particles zipping through Earth. Space probes explore planets and moons, looking for signs of past or present life beyond Earth. Mars's ancient riverbeds, the subsurface ocean of Europa, the methane seas of Titan. We are, in a sense, turning over every stone we can in this universe to piece together the puzzle of reality. Standing on the precipice of all this knowledge and mystery, we feel both incredibly small and incredibly enriched. The night sky no longer just offers twinkling points of light. It is a time machine, showing us distant galaxies as they were eons ago and connecting us to the moment of creation. The ground beneath us is not just dirt, it's ancient cosmic debris, a mix of elements made in star cores, arranged by geological and evolutionary processes into our immediate environment. We, the curious specks of the universe, will keep lighting candles in the cosmic dark, striving to illuminate more of that everything, even as it continually surprises us. The quest goes on, and the wonder deepens. To be alive as a human at this moment, to have consciousness, to have the accumulated knowledge of generations at our fingertips, and the ability to extend that knowledge, is a precious, fleeting gift. Through our minds, the universe has awakened to a sense of itself, however partial. We have the privilege of witnessing this vast tapestry and the responsibility of carrying that knowledge forward. In the end, the story of the universe is not just a tale of matter and energy moving heedlessly. It is also a human story, a story of awareness and curiosity finding a foothold in a vast cosmos. We began this journey meditating on the concept of everything. Now, at journey's end, we realize that perhaps we have only scratched the surface of everything. We close with more questions than we started, but also with a deeper reverence for existence. We sense that the strangeness and wonder of the universe will never end, no matter how much we discover. As long as there are beings curious enough to look up and ask questions, the cosmos will continue to inspire. In its darkness and its light, its simplicity and its complexity, its silence and its stories, the universe offers an endless well of awe. It is a beauty we could pursue forever and never exhaust, or without end. Darkness, silence. In the beginning, there is emptiness, a void without time, without form. All is still. No stars, no light, not even a whisper of existence. Not even time flows, for time itself has not yet begun. This nothingness is poised on the brink of everything, a deep, primordial calm. The cosmos is holding its breath, the pause before the first heartbeat of creation. From this pregnant nothingness, a subtle vibration stirs. Not a sound. There is no air for sound, no ear to hear, but a tremor of potential. In the silent void, something is about to happen. An anticipation builds, a tension at the edge of becoming. It is the moment before creation, the last instant of absolute stillness, like the hush before a symphony's first note. Perhaps it begins with a tiny quantum fluctuation, a random flicker of energy in the otherwise featureless nothing. That is enough. The seed of everything is about to unfurl. Then, a sudden expansion, an awakening. In an infinitesimal flash, the void blossoms into being. The universe exhales its first breath, and space itself unfurls violently. There is no sound. There is no outside for sound to travel in. But if one could witness this birth, it would appear as an all-pervading eruption of space. The cosmos doesn't burst into an empty room. It creates room.
Every point rushes away from every other. In that first timeless moment, the seed of everything expands from submicroscopic to cosmic dimensions. Space outraces light, not violating physics, for space itself is expanding, carrying matter and energy with it, faster than light can travel. One instant, all of existence is smaller than an atom. A heartbeat later, it's as large as a galaxy. This is the extraordinary inflation of the infant cosmos, an exponential surge that blows up the universe's size by an unimaginable factor. What was nothing becomes the foundation of all things. This is the birth of the cosmos, the Big Bang. Yet it's no ordinary explosion. It's a rapid flowering of space and time itself. In an instant, smaller than a heartbeat, the universe rushes outward. There is no center to this expansion. Every location moves away from every other. It's not an explosion in space, but an explosion of space. Before, there was no here or there. Now space-time itself unfolds from an initial state of infinite density. Time begins with this moment. Before the Big Bang, there was no before in any meaningful sense. The cosmic clock starts ticking with creation. The universe has opened its eyes. In that newborn state, everything is energy, unimaginably hot and dense. The universe is a blazing, seething fireball. Temperatures soar to trillions upon trillions of degrees. Matter, as we know it, cannot yet exist. The distinction between matter and radiation blurs. Instead, a brilliant quark-gluon plasma fills space, a fog of light and primordial particles intermixed. All the forces of nature are unified here in a single superforce. Gravity, electromagnetism, the strong and weak nuclear forces. Initially they are one, wrapped in the symmetry of the very early universe. As the universe expands and cools just slightly, this symmetry breaks. Like ice crystals forming in cooling water, the unified force fractures into four distinct forces. Gravity separates first. The gentle sculptor of space becomes its own force. The strong nuclear force splits off next, binding quarks into particles. The electroweak force remains combined a moment longer, then divides into the electromagnetic and weak forces. The cosmic symphony tunes its instruments. One fundamental note has become a four-part harmony. In the blinding hot fog, these transitions release tremendous energy and imprint subtle irregularities on the structure of the plasma. During this splitting of forces, the energy of the universe churns matter and antimatter into being. Particles condense from the energy, a churning sea of quarks and antiquarks, leptons and antileptons. Quarks pair up into protons and neutrons. Electrons zoom around. For every particle of matter, a twin antiparticle exists. They form and annihilate in rapid succession, maintaining a furious equilibrium. But as the universe cools, a slight imbalance emerges. By chance or necessity, matter gains a tiny edge. Perhaps out of 1 billion particle-antiparticle pairs, one extra particle of matter survives without a partner. When the rest annihilate each other in bursts of gamma radiation, that tiny surplus of matter remains. This infinitesimal asymmetry, on the order of 1 part in 1 billion, is enough to tip the scales. It is the reason something, matter, and not just light, fills the universe today. Those leftover protons, neutrons, and electrons, a cosmic handful of matter, will eventually coalesce into galaxies, stars, planets, and people. Already, the future is seeded in those minuscule differences. Even the early plasma carries imprints of random quantum fluctuations from inflation, slight density variations that will grow into galaxies and voids eons later. The universe is less than a second old, expanding and cooling rapidly. Quarks have locked into protons and neutrons. A seething quark-gluon plasma has given way to a swarm of hadrons, protons, neutrons, mesons. A slight surplus of protons and neutrons exists after most antimatter annihilates. In the next few moments, light atomic nuclei begin to form. About 1 second after the Big Bang, neutrinos, ghostly particles that rarely interact, decouple from the hot plasma and stream freely through space, carrying away a bit of energy. These neutrinos form a cosmic neutrino background. Trillions of them permeate every cubic centimeter of space even today, though with energies so low, their motions correspond to just a couple degrees above absolute zero temperature, that they are nearly impossible to detect. By the time the universe is about 3 minutes old, the temperature has fallen enough for nuclear fusion to occur on a cosmic scale. Protons slam into neutrons to build helium nuclei. For a brief period, the entire universe becomes a nuclear reactor, forging the first elements. Most neutrons pair with protons to make helium-4, 2 protons, 2 neutrons. A few protons remain single as hydrogen nuclei. In those first 3 minutes, the young cosmos produces about 25% helium by mass, 75% hydrogen, and only trace amounts of deuterium, lithium, and other light nuclei. This primordial nucleosynthesis sets the basic chemical recipe of the universe. After that point, as expansion dilutes the fire, the temperature drops too low for further fusion. The nuclear furnaces wink out. The elemental mix, mostly hydrogen and helium gas, now simply expands and cools with the universe. The stage is set for everything that comes next, using those simple ingredients. Still, no atoms exist yet. The matter is fully ionized, nuclei and electrons flying separately in a hot soup. The universe is a brilliant, opaque plasma of charged particles and photons. Light, photons, scatters incessantly off free electrons. It cannot travel freely. Imagine an extremely dense fog of light, so thick that any photon's path is a tiny zigzag between collisions. Space is filled with a white-hot glow, but this light is trapped, bumping around within the plasma. If there was some observer inside this early universe, they wouldn't be able to see in any direction. All would be a featureless, blinding brightness, every line of sight ending almost immediately in a sea of charged particles. The universe is opaque, like the interior of a star, with radiation and matter coupled tightly. Yet the universe continues to expand and cool. With each passing moment, the sea of plasma thins and its temperature drops. After about 380,000 years, a profound change occurs. The temperature falls to roughly 3000 K, cool enough for electrons to settle into orbits around nuclei. Protons capture electrons. Helium nuclei capture electrons. For the first time, stable neutral atoms form, mostly hydrogen atoms. This epoch is called recombination. It has 2 tremendous consequences. First, the previously trapped photons are suddenly free. Neutral atoms do not eagerly scatter visible light, so as soon as the electrons bind into atoms, the fog of the early universe clears. All at once, the photons that had been bouncing around are released to stream across the cosmos. The universe goes from opaque to transparent in a cosmic eye blink. It's as if an impenetrable mist has evaporated, revealing a vast space for light to travel. Second, the formation of atoms produces light of its own. A warm glow fills the universe as electrons settle into atomic orbits and emit photons. The entire young cosmos shines like a giant star for a brief moment. That flash of released radiation is the cosmic microwave background, CMB, the afterglow of the Big Bang. Those photons have been journeying for 13.8 billion years, stretching to longer wavelengths with the expansion of space. Today, the CMB is a faint, cool bath of microwaves about 2.7 K above absolute zero, detectable with sensitive radio antennas. It is the oldest light we can see, a baby picture of the universe covering the whole sky. But at the moment of recombination, it was an orange-white glow flooding everywhere. The universe had become transparent, and light, after ages of captivity, could finally cross the cosmos. After this release of light, a hush falls over the cosmos. The brilliant afterglow from recombination quickly dilates into the infrared and fades from human visible view as space expands. No new light sources shine yet, for no stars have formed. The universe enters a cosmic dark ages. The gas, mostly neutral hydrogen and helium, now fills space almost invisibly. If there were an observer at this time, they would be surrounded by darkness, with only the faint red diffuse glow of the receding CMB to keep them company, and even that would soon redshift into invisibility. The temperature of the background radiation slides down below the red-hot range into the infrared and radio. The neutral hydrogen gas pervading space emits only a feeble radio line at 21 centimeters wavelength when its atoms' spins flip, but otherwise it is dark. The cosmos is quiet and unilluminated, yet much is happening in the dark. The tiny variations in density left from earlier epochs, those 1 in 100,000 ripples, now begin to grow under gravity's influence. Slightly denser regions exert a stronger gravitational pull, drawing in nearby gas ever so subtly. The matter of the universe starts to gather into a web of filaments and clumps, though no one can see it yet. Over tens of millions of years, the invisible architecture of the cosmic web takes shape. Immense filaments of dark matter and gas contracting and knitting together, with denser knots at their intersections that will become the first galaxies. In these hidden cradles, gravity works slowly but relentlessly. Clouds of hydrogen gas shrink and compress. The universe is dark but not inactive. It is preparing. Like a long, starless night before the dawn, the Dark Ages set the stage for the first light of stars. And then, after perhaps 100 to 200 million years of darkness, there is light again. The cosmic dawn arrives quietly at first. Deep in one of the densest, coldest hydrogen clouds, gravity finally achieves what it's been trying to do. The gas at the center of the cloud grows so hot and dense that hydrogen atoms begin to fuse into helium. A new kind of fire ignites. A star is born. In that moment, for the first time since recombination, starlight shines in the universe. A pinpoint of brilliant light illuminates the surrounding space, carving through the darkness. This first star is likely enormous, dozens or even hundreds of times the mass of our Sun. Because without heavier elements, early gas clouds fragment into big pieces. It burns a fierce blue-white, millions of times brighter than the Sun, pouring ultraviolet rays into the gloom. In the vicinity of this newborn star, the perpetual night is ended. One by one, more stars flicker on in other contracting clouds. The first generation of stars, we call them population 3 stars, are born in small proto-galaxies, tiny infant galaxies, where the gas pooled most strongly. They cluster together in those dark matter halos, like a handful of candles kindling in a vast dark hall. These first stars live fast and die young. Being so massive, they exhaust their nuclear fuel in a few million years. But while they live, they dramatically transform their surroundings. Each massive star's intense ultraviolet light creates a bubble of ionized hydrogen around it, turning the gas back into plasma. At first, this bubble is local. Starlight is quickly absorbed by the nearby dense gas. But as more stars join the fray, the ionized zones expand. The once neutral universe is reionizing. Gradually, the light from these early stars and nascent galaxies of stars breaks apart the cosmic fog of hydrogen that pervades space. The dark intervening gas clouds that separated regions of the universe become increasingly transparent as they are ionized. Over the next several 100 million years, these growing bubbles of ionized gas merge and spread throughout space. By around 1 billion years after the Big Bang, most of the intergalactic hydrogen is reionized, split back into protons and electrons by the flood of ultraviolet starlight. The universe, which had been opaque to high-energy photons since recombination, is now mostly transparent across all wavelengths. The cosmic dark ages have fully ended. During this era, the first galaxies are taking shape. Initially, they are tiny dwarf galaxies. mere clumps of a few million stars, but gravity draws them together into larger assemblies. Small proto-galaxies merge to form bigger galaxies. The universe, once a nearly uniform glow, now becomes a tapestry of light and dark. Clusters of stars huddle into the first galaxies, which in turn group into clusters and chains. Over hundreds of millions of years, hierarchical growth builds ever grander structures. Some young galaxies are irregular or chaotic, distorted by frequent collisions. Others settle into rotating disks. Within a few billion years, majestic spiral galaxies, like our future Milky Way, appear, their pinwheel arms twinkling with billions of stars. Massive elliptical galaxies form from the mergers of smaller systems, becoming huge balls of aging stars. Galaxies congregate under their mutual gravity. They form groups and clusters, containing dozens to thousands of members. These clusters, in turn, are connected by filaments of matter, creating a vast cosmic web of structure. Everywhere, galaxies interact. When galaxies draw near, their mutual gravity can rip and morph them dramatically. Two spirals might collide and coalesce into a single, larger galaxy, often an elliptical. Smaller galaxies are gobbled up by larger ones, their stars assimilated into the bigger galaxy's halo. These collisions and mergers trigger bursts of star formation as gas clouds slam together and collapse. The universe is building big galaxies from smaller ones in a great cosmic construction project. One could think of galaxies as the cities of the cosmos, great collections of stars, gas, and dust, spanning tens of thousands of light years. In the young universe, these cities were rising everywhere and also joining into metropolitan areas, clusters and superclusters. On the largest scales, matter is strung out in an intricate pattern, the cosmic web. Thin filaments of galaxies and diffuse gas stretch across hundreds of millions of light years, with massive clusters at their junctions and vast voids between them. Astronomers have mapped colossal structures, like the Sloan Great Wall, a filament of galaxies and clusters over 1 billion light years long, and huge voids nearly as empty and as large. Up to scales of a few 100 million to 1 billion light years, we see coherent structures, filaments, sheets, and voids. Beyond that, on the very largest scales, the universe becomes nearly uniform. These immense formations are among the largest coherent objects in existence, clusters and superclusters of galaxies, strings of matter like celestial highways, each holding countless suns. Our own galaxy belongs to the local group, a small cluster within the Virgo supercluster, which is part of the even larger Laniakea supercluster, an enormous flow of galaxies converging toward a common center of gravity. The cosmic web's lattice of filaments and voids is the skeleton on which the universe's structure hangs. It formed from the slight density variations in the early universe, amplified by gravity over billions of years. Dark matter, the mysterious, invisible mass that neither emits nor absorbs light, provided the scaffolding. It clumped first, pulling ordinary matter, gas, into its gravitational wells to form galaxies. Dark matter is the unseen scaffolding of the cosmos. Though we cannot see it directly, it makes up the bulk of the universe's mass. It neither glows nor interacts with light, so as galaxies formed, dark matter shaped their growth invisibly. Every galaxy sits in a vast halo of dark matter, much larger and more massive than the visible galaxy itself. Clusters of galaxies are held together largely by dark matter's gravity. We know dark matter is there because of its gravitational influence. Stars at a galaxy's edge orbit faster than they should if only visible matter existed, and galaxies in clusters move as if an unseen glue is holding them. We also observe gravitational lensing. Light from distant objects is bent and distorted by massive invisible halos of dark matter along the way, creating rings and arcs of light that betray the presence of mass where we detect no stars. From these clues, we infer that dark matter forms filaments and halos that outline the cosmic web. It provided the gravitational wells that regular matter fell into,
Without dark matter's guiding hand, the universe's evolution would have been very different. Stars and galaxies might have taken far longer to coalesce, or might not have clustered into the rich structures we see. Dark matter neither creates light nor blocks it, it simply gravitates. It is likely some new kind of elementary particle, or particles, that interact only weakly with normal matter. Decades of experiments have yet to capture a dark matter particle directly, keeping its nature a profound mystery. But its existence is beyond doubt from the cosmic structures it allowed to form. It binds galaxies together and shepherds clusters. It is the silent partner to all cosmic creation, the universe's hidden mass.
While dark matter works behind the scenes to hold structures together, another influence grows to prominence that pushes structures apart: dark energy. For the first few billion years after the Big Bang, the universe's expansion was slowing down. Gravity was gradually tugging matter back, trying to rein in the expansion. Many scientists once thought that perhaps the expansion would eventually halt and reverse into a big crunch. But observations near the end of the 20th century shocked us. The expansion isn't slowing, it's speeding up. Starting a few billion years ago, when the universe was roughly 2/3 of its present age, the expansion rate began to increase. Distant galaxies are receding faster and faster as time goes on. Some mysterious form of energy, permeating all of space, is driving this accelerated expansion. We call it dark energy. Dark, because it eludes direct detection and understanding. The simplest explanation is that dark energy is an intrinsic property of space itself, the cosmological constant that Einstein once hypothesized. In essence, empty space has a sort of latent energy that causes it to expand. Unlike matter, which thins out as space expands, dark energy's density remains constant, or nearly so, as space grows. So as the universe gets larger, the total dark energy increases and pushes ever harder. About 5 billion years after the Big Bang, dark energy's repulsion overtook gravity's attraction on the largest scales. Since then, the universe has been in an era of accelerated expansion. What does this mean for the future? It means that galaxies not bound together by their own gravity will drift farther and farther apart. In our own local group, the Milky Way and Andromeda and satellite galaxies are gravitationally bound and will still merge eventually. Dark energy doesn't disrupt that. But beyond our local group, distant galaxies are speeding away. Over tens of billions of years, they will recede beyond our horizon of visibility. Dark energy seems to be the dominant component of the universe now, about 70% of the total energy content. It has the effect of a small anti-gravity force, very weak on local scales but significant across the vastness of intergalactic space. The nature of dark energy is one of the biggest open questions in cosmology. We often call it by that name simply as a placeholder for whatever is causing the acceleration. It could be a constant energy of the vacuum, which theoretical physics can conceive of, though with puzzlingly different magnitudes than observed. Or it might be a dynamic field that changes over time. For now, all evidence points to it behaving like a constant, the cosmological constant. If that holds true indefinitely, the fate of the universe is a continued accelerated expansion. Over extremely long times, this leads to a heat death scenario. The universe will become colder, darker, and more dilute as eons pass. Star formation will eventually cease, because usable gas is used up or driven out of galaxies. Existing stars will burn out one by one until none remain shining. Galaxies will spread so far apart that none can be seen from any other. For trillions of years, the only stars will be old embers like white dwarfs and neutron stars slowly cooling, and the occasional flare of matter accreting onto a black hole. In the far future, even black holes, which are initially the last vigorous energy sources through their slow hawking radiation, will evaporate into nothing on timescales of 67 years or more. As expansion continues, all remaining particles, mostly electrons, positrons, neutrinos, and light, thin out into a cold haze. For eons, black holes would be the main remnants of cosmic structure, emitting a faint, hawking glow as they gradually lose mass. But eventually even those last embers of the universe will wink out. No usable energy remains to fuel processes. Entropy, disorder, is maximized. The universe will approach a state of total thermodynamic equilibrium. Essentially an infinite, nearly empty void at an extremely low temperature, with particles so spread out they rarely, if ever, meet. Time, in a sense, would lose its meaning because almost nothing happens. It is a quiet, desolate finale, the Big Freeze. Another possibility, more dramatic, is the Big Rip. If dark energy is not constant but instead grows stronger with time, imagine a form of dark energy that becomes increasingly repulsive. It could eventually overcome all forces that hold structures together. In this scenario, billions of years from now, galaxies would fly apart from their clusters at ever-increasing speed. Later, gravity within galaxies would be overpowered. Stars would drift away from galactic centers. Eventually, star systems would become unbound. Planets would wander off from stars. In the final moments before the Big Rip, even atomic nuclei and fundamental particles could be torn apart as space's expansion rate diverges toward infinity. Essentially, the universe would be ripped to shreds, every bond and structure bursting as the fabric of space itself stretches violently. This fate depends on the nature of dark energy. Specifically, it requires an equation of state parameter, sometimes called phantom energy. Current observations of dark energy are consistent with $1, a constant vacuum energy. So a Big Rip seems unlikely given the data, but our knowledge of dark energy is incomplete. If future evidence suggested dark energy might strengthen, the Big Rip scenario would become a serious concern for the very far future. It would be a cosmos dying in a final, all-consuming explosion of its structure, a literally tearing end to time and space. Alternatively, the acceleration we observe now might itself be a phase that eventually ends. If dark energy were to decay or reverse sign, turn attractive, in the far future, the expansion could slow and halt. Gravity could then start pulling everything back together. This is the Big Crunch scenario, essentially a symmetric reversal of the Big Bang. If the universe's density were high enough or dark energy somehow flipped, the expansion would break to a stop eons from now and then gradually begin to contract. Distant galaxies, now long invisible, would creep back into view as they rush towards us. Over incredibly long spans, all galaxies would begin merging and collapsing toward a common center. The night sky would grow ever brighter and hotter as more galaxies, and eventually all matter, crowd into a shrinking volume. Stars might ignite in a furious burst as gas clouds compress during the contraction. Ultimately, all galactic material would coalesce, temperatures skyrocketing until everything, every atom and photon, crunches into a hot, dense state, perhaps similar to the universe's birth. This could be an oscillatory universe, perhaps to rebound in another Big Bang, a big bounce. Currently, the evidence doesn't favor a big crunch. Our universe's geometry and expansion indicate it will expand forever, and dark energy shows no sign of dissipating. But if some unforeseen physics intervened, a cyclic cosmos isn't impossible. It has a certain poetic appeal, the universe breathing in and out, eternally reborn. There is yet another subtle doomsday scenario, vacuum decay, sometimes nicknamed the Big Slurp. This relates to our understanding of quantum fields. It's conceivable that the ground state of our universe, the vacuum, is not truly stable. We might exist in a false vacuum, a local minimum of energy that could, via a quantum tunneling event, transition to a lower energy state, a true vacuum. If such a vacuum decay occurred, a bubble of the new vacuum would nucleate somewhere in the universe and then expand at nearly the speed of light. Inside that bubble, physics could be radically different. Fundamental constants,
particle masses, and forces might take on new values. This bubble would annihilate anything it encounters as it rewrites space. Because it moves so fast, one wouldn't see it coming. One moment the world is as normal, the next, the bubble wall rushes past, and everything as we know it is transformed or destroyed instantly. It's a very exotic scenario, and most calculations suggest if our vacuum were prone to decay, it likely would have happened billions of years ago, or won't happen for trillions of years to come. It requires specific and uncertain conditions in particle physics, notably involving the Higgs field's potential. Current measurements of the Higgs boson hint our vacuum might be metastable on timescales vastly longer than the current age of the universe. So while vacuum decay is a physicist's worst-case ending, it's not something we lose sleep over. If it were to occur, it would be the ultimate wildcard end. The universe as we know it abruptly vanishes, replaced by something else entirely, with no warning or remnant. So, the universe's story may end in fire or in ice, in ripping apart or in a quantum whisper, or perhaps in ways we cannot yet imagine. Each scenario is an ending written into the equations of cosmology, but which, if any, will come to pass remains unknown. Our best guess, based on current knowledge, is an eternal expansion leading to heat death. Yet the cosmos has surprised us before. The acceleration by dark energy was unforeseen until observed. There may be new physics awaiting discovery that alters the final act. In truth, the ultimate fate of the universe is still a mystery, and it is fitting that here, the universe, through the thoughts of the conscious beings it produced, contemplates how it might end. It's as though the cosmos itself wonders about its finale, using small intelligences within it, like us, to explore the question. But whatever the end might be, it lies unimaginably far in the future. Right now, the universe is alive with galaxies, stars, and perhaps life. The story is ongoing, and we find ourselves in a chapter rich with possibility.
Consciousness. Now we arrive at one of the most marvelous phenomena in the universe. Out of non-living matter, through the gradual work of complexity and evolution, awareness has emerged. How astonishing that, in a cosmos governed by impersonal physical laws, collections of atoms have developed the ability to contemplate those very laws, and to feel joy and sorrow, wonder and intent. With the appearance of life and mind, the universe has gained eyes to see itself and minds to reflect upon its nature. Tiny, fragile living beings on insignificant worlds gaze up and discover the fire of creation in the sky. In them, cosmic evolution has become self-aware. Life began, at least on one small planet, Earth, when chemicals assembled into self-replicating structures. Exactly how is still uncertain. It may have been a stroke of chance in a warm pond or deep-sea vent, or a gradual emergence aided by the planet's chemistry. But the basic ingredients were forged long beforehand. The carbon, oxygen, nitrogen, and other elements essential to life were synthesized in stars and scattered by supernovae. Earth formed from cosmic dust enriched by those elements, and life's molecules drew upon that bounty. Water, a molecule of hydrogen and oxygen common in space, became the medium for biology's experiments. Single-celled organisms arose over 3.5 billion years ago in Earth's ancient oceans. They were simple, lacking nuclei, yet they metabolized and reproduced, launching the great tree of evolution. For billions of years, life remained microbial. Those microbes transformed the planet. For instance, cyanobacteria flooded the atmosphere with oxygen. 2.5 billion years ago, an early example of life reshaping its environment. Complexity built gradually. Cells joined into colonies, then into multicellular organisms with specialized tissues. By around 540 million years ago, the Cambrian explosion, a dazzling variety of multicellular life forms filled the seas. Some ventured onto land, plants first, then animals. Life developed structures like eyes to sense light, limbs to move, brains to process information. Evolution, driven by natural selection, explored an astonishing design space, resulting in creatures from dinosaurs to dragonflies. Among the myriad life forms, one lineage, primates, produced a species with exceptional cognitive abilities. On Earth, that species is Homo sapiens, us. We are latecomers, arriving only a few 100,000 years ago. In that short time, we leveraged intelligence to alter the planet and peer into the cosmos. Through us, the universe has learned about its own origins. We discovered the cosmic microwave background, essentially, the universe's baby photo. We identified the chemical elements in the stars, the same elements found in our bodies, confirming our intimate connection to the cosmos. We've sent spacecraft to neighboring planets and listened for faint whispers of the universe, like gravitational waves from black holes merging billions of light years away. Humans are made of the universe's matter. The iron in our blood was forged in stars, the calcium in our bones in stellar explosions, the water in our cells likely delivered by ancient comets. And now that matter can think and learn. In us, the Stardust has become self-aware. Are we alone in this? The cosmos is vast, and the conditions that gave rise to life on Earth may exist in countless other places. There are hundreds of billions of stars in our galaxy, and trillions of galaxies. Surely, Earth is not the only world where chemistry blossomed into biology. We have already discovered thousands of exoplanets orbiting other stars, some in habitats where liquid water, and thus Earth-like life, could exist. Organic molecules, the building blocks of life, are found in interstellar clouds and meteorites. It seems the universe is biased toward forming the ingredients of life wherever it can. Simple microbial life might be common. Perhaps in the subsurface oceans of icy moons in our own solar system, life has independently arisen. But intelligent, technologically capable life might be far rarer. After all, in Earth's 4.5 billion year history, only one species has attained the ability to send signals into space. If other civilizations had arisen frequently in our galaxy's 13 billion year history, we might expect that some would have spread or made their presence known. The silence of the stars, sometimes called the Fermi paradox, could mean many things. Maybe intelligent life is indeed very scarce, or maybe civilizations are short-lived, or perhaps they communicate in ways we haven't recognized, or simply the galaxy is so immense that our nearest intelligent neighbors are extremely far away. As of now, we simply don't know if we are alone. It is both exhilarating and humbling to realize that, for now, we are the universe's only known self-observers. That status imparts a sense of preciousness to consciousness, ours and that of any other beings that may exist. Consciousness itself remains a mystery. How does the coordinated firing of neurons give rise to subjective experience, to the feeling of I am? This is the hard problem of consciousness that neuroscientists and philosophers grapple with. From the cosmic perspective, one can speculate. Perhaps consciousness is an emergent property when matter organizes in very complex ways, like in a brain. Or maybe there is some fundamental aspect of nature that includes mind. Some suggest even elementary particles might have proto-conscious qualities, an idea called panpsychism. If the latter were true, then as the universe became more complex, consciousness gradually woke up, more fully within it. If the former is true, then consciousness is an exceedingly rare cosmic phenomenon, requiring a fortuitous chain of events and structures, like brains, to exist. Either way, consciousness is a way in which the universe, otherwise governed by simple physics, has something internal, something it feels. Through conscious beings, the universe experiences qualities like color, sound, pain, and love, which otherwise would not exist. A rock orbiting a star doesn't know it's in orbit. A star doesn't know it's shining. But we, conscious entities, do know and appreciate these things. Our minds can hold models of stars and galaxies. In a sense, tiny portions of the universe, our minds, have become reflective, able to contemplate the whole. Consciousness also allows the universe to ask questions about meaning and purpose. Questions that in a purely material sense might be moot, yet that matter deeply to the conscious creatures themselves. We, for instance, seek purpose in our small lives amid this vast cosmos. Science tells us how we came to be. It doesn't tell us why, if there is a why. Many thinkers suspect that questions like, why does the universe exist? Or, what is the purpose of consciousness? May not have answers in the way we hope. The universe might just be, without deliberate purpose. Yet here we are, imbued with love, curiosity, and longing for meaning. In a way, one might say the universe's purpose, if any, is what we, as parts of the universe, make of it. By our very nature, we invest the cosmos with meaning. When we create art, discover scientific truths, show kindness to one another, those acts give the universe experiences it would not otherwise have. Through us, the cold equations of physics bloom into poetry and empathy. Through us, the universe can admire itself and say, it is beautiful. We humans, so small and temporary, are a way for the cosmos to know itself. We are aware that we are made of star stuff and that we live on a mote of dust suspended in a sunbeam, to borrow a phrase. We've also realized that our minds are the result of billions of years of cosmic and biological evolution, a precious, transient flicker in a very old and vast space. Each of us is a tiny fragment of the universe that for a brief moment is self-aware. And we carry the heritage of the entire cosmos within us. Consider the atoms in your body. The hydrogen in your drinking water was made in the first minutes after the Big Bang. The carbon in your cells was forged in some star billions of years ago. The calcium in your bones was fused in the heart of a massive star and scattered in a supernova. The iron in your blood came from the violent death of a star. The phosphorus enabling your DNA was built in cosmic furnaces as well. We literally embody cosmic history. Stardust runs through our veins. When we look up at the night sky, we are gazing at our kin. The stars are our distant cousins, related by common origin in the Big Bang. The light that reaches our eyes triggers thoughts in our brain, a star's photons, causing a pattern of electrical signals in a mammal's nervous system. How extraordinary that a thermonuclear reactor millions of light years away can set off a spark of thought in a being on Earth. Through those thoughts, the universe is, in a small way, conscious of itself. In fact, when you consider it deeply, there is no sharp separation between us and the universe. We are not observers outside the cosmos. We are an integral part of it. Our bodies are composed of the universe's matter. Our thoughts arise from physical processes in our brains that obey the universe's laws. We emerged from this cosmic system and are immersed in it completely. The universe is our larger body, and we are like its tiny self-aware cells. At this point in the story, the universe, through human minds, can even attempt to summarize its own journey. In doing so, it turns the mirror on itself. We, on our pale blue dot, have reconstructed much of cosmic history. We have mapped the afterglow of the Big Bang. We have observed galaxies across cosmic time and seen back to when the first stars were kindling. We've understood how elements were born in stars and how Earth came to be enriched by them. In short, we have become the historians of the universe, cataloguing its saga. And we are the universe's storytellers too, giving narrative and meaning to events that on their own are neither good nor bad. They simply are. The rise of life, the collapse of a star into a black hole, these just happen, but through conscious eyes, they become stories of wonder, tragedy, and transformation. Now, having journeyed from the beginning of time to speculations about the end, and from the simplest particles to conscious beings, let us conclude with a moment of reflection. Take a slow breath. Feel your lungs fill with air. Much of that air was once inside of stars and will be part of other life after you. Feel your heart beating, a rhythm that connects you to the first heartbeat of the cosmos when it expanded from silence. In this very moment, you are the product of the entire history we've recounted. You are ancient hydrogen and stardust shaped by gravity and chemistry, given form by biological evolution, and endowed with a spark of awareness. The silence that we imagined at the very beginning still echoes within you in the quiet moments between your heartbeats. The darkness that once enveloped the cosmos is the same darkness behind your closed eyelids when you contemplate. But now the silence is filled with the potential for thought, and the darkness can be lit by the imagination.
Stardust remembers. The atoms of your body hold memory, not conscious memory, but the record of cosmic events encoded in their existence. Each heavy element remembers a star that lived and died. In a way, when you think about the universe is remembering itself. Your brain's atoms clicking into patterns that mirror the cosmos outside. Time flows through us. We are part of the grand progression of entropy and evolution. The arrow of time that began at the Big Bang runs through every cell in our body. The blood circulating in your veins right now was forged in a sequence of events going back to the beginning of time. You are a wave traveling through the ocean of time, temporarily taking shape as an individual crest before merging back.
The universe is not far. It is here. It is in your breath, in your bones, in the light that falls on your eyes. It is the ground beneath you and the space around you. We carry the universe within us, and we walk within the universe. There is no separation. The cosmos is our home and our essence. When the universe speaks, through equations or photons, we can understand because we too are expressions of those same underlying laws. When we cry out in joy or despair, that is the universe, in a small part of itself, experiencing emotion. Our narrative nears its end, but the universe's narrative continues, unfinished. The story of the cosmos is still being written, in the motions of galaxies, in the birth of new stars, and perhaps in the endeavors of conscious beings like us. We find ourselves at a wondrous juncture. We can look back and reconstruct much of cosmic history, and we can look forward and ponder cosmic futures, but we are still at the dawn of understanding. There remain deep mysteries, dark matter, dark energy, the origin of it all, the purpose of consciousness, that we have yet to unravel. The universe is unfinished, not just in the temporal sense, with events yet to happen, but in the sense that its truth is not yet fully known. There are pages left to read, and perhaps new pages still to be written by the acts of intelligences. If we last long enough to spread life beyond Earth, for example, we will be adding a new chapter to the universe's story. We end where we began, in darkness and stillness. Picture the void before creation once more, that expectant nothingness. Picture the stillness after a possible end, the quiet of a heat-dead cosmos, or the silence of a post-Big Crunch void. In some sense, they are the same silence. The universe may end in silence as it began in silence. But between those two silences, what a symphony of being has played out. A symphony with movements of blazing brilliance, the era of stars, and deep recesses of melancholy, the cold depths of space, with themes that intertwine matter and energy, creation and destruction, simplicity and complexity. We have been part of that symphony, a brief, delicate violin solo in a grand orchestra. Without us, it would still be magnificent, but with us, it can be appreciated from within. We are the universe listening to its own music, even as we play our small part. The narrative pauses now, but it does not truly stop. Even as these words cease, stars will continue to shine and atoms will continue to collide in the vast reaches of space.
The universe goes on, ever unfolding. And you, a child of the stars, go on as well, carrying the knowledge and awe gleaned from this story. When you next step outside on a clear night, perhaps you will feel more connected to those distant points of light, knowing what they are and how they came to be. Perhaps you will sense, as ancient stargazers did, that the universe is not a cold stranger, but a deeply related entity, our ancestor, our substance, our home. Listen, in the quiet night, under the cosmic ocean of stars, you can almost hear it, the heartbeat of the universe. It is the blood pulsing in your ears, and the echo of gravitations and vibrations that ripple through space. It is the memory of the Big Bang imprinted in your very atoms, and the faint music of all the stars carrying on through the dark. In that soundless music is a truth felt if rarely spoken. The universe is alive in us, and we are alive in the universe. We are not mere observers, we are participants. Its story is our story. Its beginning is our beginning, and its future, though unknown, is tied to us as well, for we are part of this cosmos. The tale of the universe is thus far a tale with no known ending, an unfinished book, an open-ended quest. We find ourselves on one shining page of that epic, aware of our role and eager to read on. The universe is, forever, unfinished, an ever-unfolding mystery in which we, for a fleeting moment, get to partake. And in that fact lies profound hope and meaning. The song of the universe goes on, and we, conscious flecks of stardust, get to harmonize with it, adding our verse to the cosmic chorus. The story continues, and we are part of it, always. It is unfinished.